Hello, and welcome to Beyond the World of C++. I'm David I, and I'm excited to guide you through this video course, which will teach you how to use the more advanced features of C++. This video course contains a lot of information. First, I'm going to give you some basic instructions to get you started, and then I'll turn it over to Bruce Eckel, one of the world's leading experts in C++. Here's what we'll cover. After the introduction and review lesson, we'll show how to use multiple inheritance to build new classes, how you can use I/O streams for easier input and output. We'll introduce containers and iterators as invaluable ideas for object access and storage, templates as a better way to build generic types, and we'll also cover some special member functions and programming techniques in C++. Then we'll cover the basics of exception handling to allow you to build robust C++ applications. And with Lesson 9, you'll go back to the workbook to cover the latest C++ language developments. We've designed this video, workbook, and sample programs to work together as a comprehensive training course. After watching a video lesson, turn to the corresponding chapter in the workbook. At the end of each chapter, be sure to try out the example programs and work on the exercises provided for you. In order to get the most from this course, you should already know about abstract data typing with classes, single inheritance, and polymorphism with virtual functions, as well as how to use the new and delete operators. Before going further, stop the tape and take a look at the README file on your disk for the latest information. Then be sure to read the introduction and review chapters in the workbook. The review chapter introduces example classes and programs that will be used throughout this course, such as the XBAG and string classes. After you've gone through the introduction and review chapters, I'll see you back here in Lesson 2 where we'll cover multiple inheritance. See you then. Hi, welcome back. Inheritance, also called subclassing, allows you to create a new class using the properties of an existing class while adding additional new capabilities. Multiple inheritance allows you to take the best parts of several classes to build a new class that is required for your application. Bruce will show you how.
Let's look at multiple inheritance. Multiple inheritance has kind of a sordid history because it was the first feature that was added to C++ after the language came out originally. So the problems with multiple inheritance, well, obviously you've seen what it is. It means inheriting from more than one base class. The problems are that you can have duplicate subobjects. It's ambiguous when we're upcasting, and I'll show you all these things. And to solve these problems, we use what are called virtual base classes. So multiple inheritance means that you get a new type from more than one base type. Syntax is exactly what you'd expect. The constructor initializer list, same thing. You put more base class constructor calls in. And in your base class list, you simply list all the members of the base, or all the base classes. But it introduces some ambiguities and some odd situations. Okay, to get a little bit of perspective on multiple inheritance, why we absolutely had to have it, or why people felt like they absolutely had to have it. This is while C++ was still really within AT&T and under the control of AT&T, and enough people within AT&T could kind of bring force to bear on Strustrup and his team to say, we got to have multiple inheritance. It just has to be this way. Okay, Smalltalk is the most successful object-oriented language before C++. Smalltalk is a language that somebody created from the ground up. They said, we will create an object-oriented language from scratch. Okay, that's one aspect of a pure object-oriented language. It's object-oriented from the ground up. C++ was created from C, and it is often referred to as a hybrid language because it's created from a procedural language. It's taking a procedural language and turning it into an object-oriented language and simultaneously not breaking the bulk of C code. So it's a pretty good trick. Also, it means that everyone who knows how to program in C can fairly quickly get up to speed on C++, which is really the reason it was so successful. That and the fact that the original C-front that came from AT&T was a translator from C++ to C, so that meant that it could quickly be ported to most platforms. So those two strategies have made C++ as successful as it is. Okay, with Smalltalk, as I mentioned earlier, you have all the classes are based in a single hierarchy. And at the root of that hierarchy is a class called object. So when you hear the term object-based hierarchy, it doesn't mean object-based in some sort of abstract sense. It means that at the root of this hierarchy is a class called object. That's all it means. But we refer to object-based hierarchies as single monolithic hierarchies, and the concept came from Smalltalk. The thing about Smalltalk is that you can't start your own class tree. You always have to start from the existing class hierarchy. So any creation of new classes in Smalltalk always involves inheritance. So you simply find a place on the tree which most closely fits your needs, and then you inherit from it, and you create a new class based on that, which means that everything has the same root. Everything always goes back to object. Now this is very convenient in Smalltalk because if you make a container class, and as I talk today, you'll begin to see more and more how important container classes are and how fundamental they should be to your programming. As you use container classes in Smalltalk, a container class will contain things of type object. Now our XBAG has held things of type void star, because that is, well, I suppose in C that's sort of the root of all objects, but that doesn't work really well. Anyway, there's void star, which we're holding there. Well, Smalltalk's got an advantage because it can hold things of type object, and in the base class, this abstract base class object, you can have a certain set of functions that are always there and always inherited throughout your hierarchy. So it's guaranteed that you can do certain things in Smalltalk with any container class. Now, the advantage of this is that because they have a single monolithic tree, if you say, I want a container to hold shoes, well, shoe has got to be derived from object because that's the only way you can make a new class, is deriving it from this monolithic hierarchy. So if you have a container class that holds objects, it will also hold shoes. No problem. The thing about C++, where we run into difficulty, is that C++ can create many hierarchy trees. You can start your own hierarchy. In fact, this is one of the advantages, is that you can buy class libraries from lots of different people, and they don't have to depend on inheriting from some single hierarchy. They can invent their own world if they want to. So because of this, for completeness, we want to be able to see if we can have many hierarchy trees. We want to be able to inherit from several hierarchy trees at once. With C++ and with multiple classes, we run into a problem, and that is, which is where we really need multiple inheritance. This is, in my mind, the real clear driving force. I mean, you can think of multiple inheritance, and a lot of the examples that you get will be, some of the worst ones I've heard are, you have a frog prince. So you need multiple inheritance to make a frog prince. A lot of the examples that you will see, in fact, I have not been able to come up with an example that is really clear to me to say, well, here's a situation where you really absolutely positively have to have multiple inheritance. I have been working on it for a while because I'd like to be able to present it to people, but I haven't been able to come up with one that just hits me in the face and says, this is a great example of multiple inheritance. You know, I keep coming up with exactly the same kind of things. Frog prince or rum raisin ice cream, you know, just mixing things together. But there's other ways that you can do that. Well, the real need for multiple inheritance, in my opinion, the thing that has driven it is the idea of container classes. So you buy a container class library from somebody, and their container class library holds, well, they create an object-based hierarchy. And those of you who have been working with the Borland compiler for a while and looked at their container classes, they do exactly the same thing. They have, well, the old-style container classes, the pre-template container classes, have an object-based hierarchy. And they have something at the base called probably T-object or something like that. Okay, so the idea is they have this hierarchy, and all of their containers hold things of class T-object. Sounds good. All you have to do when you create an object that you want to stick into one of their containers is inherit it from a T object. Sounds good so far. Now the problem comes along. Suppose you buy a class library from vendor B, say he's got a shape library, and you've got vendor A's container classes, and you want to put vendor B's object into vendor A's container classes. Well, vendor A has got his object-based hierarchy, and vendor B has their shapes, and they've got all those things. Well, how do you put a shape or a circle or whatever into a container class that holds objects? Well, you have to have something that is both a shape and an object, multiple inheritance. Okay, this is what happened. This is why people were saying, we got to have multiple inheritance because we have all these libraries and we want to combine them in particular so that we can use container classes easily. Okay, the thing about this whole worldview is that once we got templates, which you'll see a little later, a template is a way to make a parameterized type. That is, a type with one or more of its arguments, one of the things that it holds or deals with, unspecified at the time that you create that class. So with a template, we can say, and I'll do this later on in the day, I will create an X bag that will hold anything. It will hold things of some unspecified type. And then when I'm ready, I can make an X bag to hold shapes. And that X bag is actually created for me at the time to hold shape objects, and it knows everything about shapes. And so when you destroy a shape, it destroys the shape properly. So that's all taken care of for you. Strostrup foresaw this in his very first book, in the book that people learned from initially, and he created a way to do parameterized types using preprocessor macros. The thing is, once you have templates, it removes the need to worry about multiple inheritance when using container classes. And it turns out that the rest of the things where people have been struggling to come up with examples so long, the rest of those situations we can kind of work around. And now all of a sudden it looks like, well, gosh, maybe multiple inheritance, maybe we really didn't need to do this because we have solutions for all these things, and in many cases, like in templates, much more elegant and useful solutions. Anyway, I will show you how containers work. Here's an example. Vendor A's got an object-based hierarchy, and they have a list which contains objects. Vendor B has something called, say, a bit image. And so we use multiple inheritance to create an object and a bit image called an O-bit image. And now, since this is of type object, it can be stored and retrieved from this list. Of course, with a template, what you would do is you wouldn't have an object-based hierarchy. You would simply create a list that held bit images, and you would remove this and this from the scene of things. So much easier to deal with. Okay, now there are certain design needs for multiple inheritance, perhaps, and you can find one of these inside of the IOStream library, where you have a base class called iOS that's inherited from into iStream and into OStream, and sometimes you want an object that is both an iStream and an OStream so that you can read and write to this object. Anyway, what are the problems with multiple inheritance? One is that we can have duplicate sub-objects. So in the example that we just saw, what happens when we inherit iStream from iOS? Well, all the data members in iOS are brought into iStream. So that object is basically duplicated inside of iStream. It is also duplicated inside of OStream. Now, when we do multiple inheritance with iStream and with OStream, we end up with two iOS objects in our IOStream. So there's a duplicate subobject there. Sounds like it might be a problem. The compiler can deal with some of the issues, but in general, it's not a good idea. Not only does it take up extra space, but it introduces an ambiguity in that if you're doing something when you're dealing with an IO stream and it deals with an iOS object, which iOS object are you talking about? Sometimes it makes sense to have two different ones, but sometimes you want to be dealing with a single unified iOS object. A second problem is, what if you cast an IO stream up to an iOS object. So let's look at this again. Okay. So if you have an IOStream object and you take the address and cast it up to an iOS object, well, what this does is it should return a pointer to the iOS object that is contained within the IOStream. Now you ask which iOS object, since we have two of them contained in the IOStream. Compiler throws up its hands and it says, I don't know, that's an error. If you tried to upcast from IOStream to an iOS object in the model that I'm currently giving you here, you would get an error message. So that's another problem. So let's look at an example here. So we start with the base class. I'm using structs here, so I've just eliminated the need to put public in there. So I have a base class with a pure virtual function here called v. And I derive from base into D1 and D2, and I redefine that function. And then I have some multiple inheritance here. Now, what happens down here? OK, I can create, since D1 and D2 are derived from B, I can easily upcast D1 and D2 to B. That's fine. So I'm creating an array of pointers to base. Now the problem is, what happens when I create an MI object, which is multiply inherited from D1 and D2, and I try and upcast it to B? Well, D1 contains a base subobject, and D2 contains a base subobject. So if I multiply inherit these things in MI, and I try and upcast that, the compiler doesn't know which subobject it's supposed to return the pointer to. Is it supposed to return it to the subobject base inside of D1 or D2? OK, so that's a problem. And in addition, what would it mean if it chose to cast it to one or the other? What would it mean when I called the virtual v function for that? It's ambiguous. OK, so to solve this problem, what we do is overload the meaning of the virtual keyword. Fortunately, it's only overloaded once. We've got virtual as you've come to know it, and now we have virtual base classes. What you have to do is, if you have, this is where it gets a little tricky, if you have a class that you know later on is going to be used in multiple inheritance, if you have clairvoyance and you know, say, these classes are going to be multiply inherited, which suggests that when you're using multiple inheritance, you had better have control of the whole design. So you better be designing multiple inheritance in from scratch to solve some particular need of yours. So if you're doing this, and you see this happening, you say, well, I'm inheriting this base class, and the class that I'm creating might be used in multiple inheritance. So I will inherit this base class as a virtual base class. This means that if the class that you're creating is now used in a multiple inheritance scheme, that base class that you've inherited virtually, only one subobject of that will appear, regardless of how many would normally appear if you weren't doing virtual inheritance. Now this is done with some pointer magic, because instead of laying the class directly in, the compiler puts some sort of a pointer inside there. And so all of the classes that have virtual base classes, they simply have pointers to that virtual base class. And now, when you create the multiply inherited class, you have to, somewhere that base class has to be initialized, and then all those pseudo subobjects, now their pointers are pointing to that single subobject. Now there's no ambiguity. Say if you do an upcast, there's no ambiguity because you only have one subobject of that type. So let's look at an example. So we have a base class, same situation as before, but now I use virtual base classes, there and there. I still have to do something when I use multiple inheritance. When I redefine this v function, I'm going to want to explicitly disambiguate it, because otherwise, if I do not include this line here, then if I were to call v, the compiler still wouldn't know, do you want D1's v or D2's v, because there's an ambiguity there. So I solved this problem by redefining v in my multiply inherited class, and I make a specific call to one of the base class versions of v to disambiguate that. So now we don't have a problem. Okay. So here, this line works okay. because when I ask it for the pointer to the base class subobject, it knows there's only one, because that's a virtual base class. So only one subobject of that type shows up. This is all fine now. But not so fast. It's not quite so simple as that. What I've shown you here has a default constructor, so that's OK. The thing is, it gets a little stranger when you have a virtual base class that has a constructor which is not default, has arguments. And that is because, OK, we start with the base class. We inherit it into several derived classes virtually. But remember that those are just pointers. Well, in effect, they're just pointers. There's some pointer magic in here. Instead of a full subobject being placed in all these derived classes, there's pointers to it. Well, which of those classes, when you do multiple inheritance, which of those classes is responsible for creating the subobject? You know, is it this one, or is it this one, or is it this one? I don't know. You don't know which one is responsible. I mean, you have to decide that when you create the multiply inherited class. So this requires a new term, and that is the most derived class. The most derived class is the one that you're currently in right now. In particular, when you're in the constructor for that, you are in the constructor for the most derived class. I mean, you can't think about classes that are derived from you, because you never know what class is derived from you. But you know that you're the furthest out on the inheritance hierarchy right then. The most derived class is the one that is responsible for initializing the virtual base class. So when you are in the most derived class, you are responsible for calling the constructor for the virtual base class. Now this is kind of weird, because it means that no matter how far out on the hierarchy you are, even though that virtual base class might be buried 10 layers below you, you are still responsible for knowing about it and for initializing it. Is this the kind of thing you want to saddle your class users with? You know, when they inherit it from it, that means they have to know not just about what the base class is right behind you, but what is going on in the entire hierarchy. Kind of a, yeah. Well, let's look at it. Here's a base class that has an integer argument in its constructor. Now, inside of D1, which is derived from base virtually, okay, just like you would normally expect from a base class, here everything is fine. We have to call the constructor in the constructor initializer list, okay? Similarly with D2. Now the thing is, inside of this constructor, I'm in the most derived class, and I'm responsible for initializing the virtual base. Now it doesn't look, it's no problem, because that is the direct base class. Direct base class is the one that's right behind you. And normally we are responsible for initializing our direct base class. The weirdness gets when you're dealing with an indirect base class that is virtual. Okay, now in my multiple inheritance, I've got D1 and D2, and yet, even though those are not direct base, I mean, even though base is not a direct base class of MI, I'm still responsible for creating it. If I don't put this in, the compiler will give me an error message. It says, I can't find a default constructor for that virtual base class. So it can't initialize it. So you have to explicitly put this in, even though it's not a direct base class. And if we go one more layer out and inherit X from MI, we are still responsible for initializing that virtual base class, even though it's now, what, 2-3 levels deep. Curiouser and curiouser. Okay. So everything else works okay. This bothered me for quite a while, because I thought, gosh, how am I ever going to use multiple inheritance and deliver a library to somebody, or even within your company? If somebody else is using your library, you have to say, oh, by the way, there are these weird things called virtual base classes. And remember that you, here in this room, you are the people who are the library designers. You're the architects. You're the people that kind of have the vision to create good class libraries. And the people that are using them are not necessarily, well, they don't really want to know all the internal details. They just want to be able to solve the problem that they're trying to solve. And do you want to explain multiple inheritance to them? So, okay. The thing is, it turns out that there is a way, if you are using multiple inheritance, to tie off the virtual bases by using a default constructor. Basically, this is simply suggesting if you ever have a virtual base class and you're using multiple inheritance this way, always make sure that your virtual base class is designed such that it can have and use a default constructor. Because if it doesn't, remember the consequences, and that is you're going to have to explain to anybody who inherits from your class all about multiple inheritance and how they have to initialize the virtual base class. Here's my default constructor there. And then in my various derived classes down here, I don't have to worry that there is a virtual base class. It's hidden from me now. Okay. I have heard people who work with AT&T say that you should not use multiple inheritance before you've been programming with C++ for 3 years. I think they're joking, but I'm maybe not. Actually, that's a big company, and there's a lot of C++ programmers within it. And so maybe they would really prefer that people don't do that because it would reduce the number of questions that they get. But you should realize that it is not an everyday feature. If you see a place where you think multiple inheritance ought to be used, look twice and say, gee, should I perhaps be using composition? Now, if you want to combine more than one thing, remember that with composition, you can put in a bunch of member objects. You know, it's like you wouldn't want to multiply inherit car from engine and windshield and wheels and radio. You would want to use composition. It makes more sense, and it works out much nicer. So remember that when you're looking for things that maybe should be multiple inheritance, maybe they should be composition instead. And in particular, the situation that I have come to believe was the real driving force behind multiple inheritance, which is the need to be able to easily use container classes, that has been removed because of templates.
This concludes this lesson on multiple inheritance. Oh, and in case you're wondering, we'll cover templates in Lesson 5. Before going on, be sure to review the examples and exercises in the workbook. In this lesson, Bruce will cover I/O streams. I/O streams give you a consistent and easier way to deal with input and output, in-memory formatting, and file manipulation for all different types of data. Much better than the old standard I/O capabilities of ANSI C.
Now, a lot of you have seen and used I/O streams, the simple stuff. What I want to show you now is some more of the nifty features, and in particular, something that I only discovered, again, from the person who wrote the I/O streams library. He pointed this out at one of the ANSI meetings. And it's a real powerful feature, and it's dealing with the underlying stream buff. And I'll explain that in a second. But once you see this, I hope that you'll start doing lots of interesting things with I/O streams. So we'll look at basic ideas of how to use them, look at, and in particular, this using the underlying stream buff and what's going on there, how the shift operator works, in particular, how the compiler parses these expressions with lots of shift operators stuck together. And once you understand that, then you can understand how to write your own shift operators for I/O streams. And the concept of a manipulator, which is like endline is ENDL, that's a manipulator. It's a function that you stick in one of these streams and have it, and how they work, and how to write your own. And then an example using the constream library in there that Borland wrote, and that's a good example if you want to see how to create your own, how to extend I/O streams for your own particular needs. So I/O streams are accepted into the standard C++ library. They're part of the standard now. There wasn't really any question because pretty much from day one, everyone has had an I/O stream library. You're familiar with the left and right shift operators, the real simple stuff. We're going to go a little deeper, going to exploit some of the features of I/O streams, in particular the underlying structure of I/O streams, and this idea of a stream buff, which is really potent, and show you how to extend the library by creating your own I/O stream features. In I/O streams, you got two layers. One of them deals with formatting. That's the iOS layer. That deals with how characters are converted back and forth. The other is buffering. So they've separated the two things. Formatting, translating characters in and out. Buffering, holding the characters in the meantime. The two are really separate concepts because your buffering may happen, in some weird place. It might come from, perhaps you could extend I/O streams to handle serial communication, and your buffering might be in a particular place, something like that. So when you want to deal with your high-level operations, you derive a class from iOS. When you want to deal with the buffering layer, you deal with the stream buff. The two classes are connected. So you've got two separate classes in I/O streams. The two classes are connected by a pointer, which is generally called, just referred to as BP. And the iOS class always has a pointer to a stream buff. So iOS class handles the formatting, and it uses this stream buff pointer to store its characters and to get them out. So if you want to make a new I/O stream, a set of I/O stream classes for your own particular needs, you derive a buffering component if you want to change the way buffering works. You don't have to. You can use the existing stream buffs. But you can derive a buffering component from stream buff and change the way that works and redefine the virtual functions. And I'll list some of the important virtual functions that deal with putting characters in and getting them out of the buffer. And you can derive a formatting component from iOS. And then inside of the constructor for your iOS, you set your BP, which is a protected pointer, you set your BP to your new buffering component. That's how it works. And a little later in this section, I'll show you how to do that. First, I want to show you some typical examples of I/O streams and how to improve them using the stream buff. First off, everything that you're familiar with, CIN, COUT, CERROR, all are the equivalent of standard I/O. They're declared in iostream.h. You include that, and you use the things. Okay. File manipulation. If you're not using I/O streams now for doing file manipulation, you want to start because it just makes life so much easier to open and read and write things. All you have to do is create an fstream object, whereas with standard I/O, you create a file pointer, you call open, do all this kind of stuff, check it and everything. You do it in one fell swoop, and then, of course, you have to close the file when you're done with it. In one fell swoop, you create an fstream object, and it does the work of opening the file for you. And when it goes out of scope, of course, the destructor is called, and that closes the file. So all you do is create this object, and you're done. Much easier. There are specific types of fstreams, inherited, of course, from fstream. There's an ifstream to create an input file stream, and an ofstream to create an output file stream. There is a default constructor argument. The second argument tells what type of file you want to create, and it defaults to text file. But if you want to create a binary file, you simply insert that default argument. OK, let's look at a textbook example. What I do is I take the first argument, and this is just a file copy. So I make an IF stream from the first argument and an OF stream from the second argument, and of course assert them to make sure that they've been opened properly. This is another feature of I/O streams, which is really nice, and that is it returns an integral argument to indicate whether it's been opened or not. So once I open them, I create the character. I define a character C, and I do a get and a put. So I get a character from one file, put it to another. Now, actually, in the file, there's some underlying buffering that's going on, so that this isn't quite as awful as it looks. It's still about as bad as you could possibly do it. Get a character, put a character. However, what the underlying fstream is doing is it's got a buffer, and it's going to read, it's the normal file buffering that's going on. It's going to read a chunk of the file and bring it into memory, and then you're just moving it back and forth. However, it's about the most inefficient way that you can write the code. An optimal solution, of course, would be if you had underlying knowledge of the hardware, and you could go in and do something, you knew exactly how big, say, the cache on the disk controller was, or something like that. You go in and mung with the hardware, and you could do some really fast file copies. Of course, an optimal solution generally isn't a portable solution. So what I want to show you is a portably optimal solution, and I'll do this by accessing the underlying stream buff. The stream buff, remember, is where the characters are actually stored. What I will do is there's a special function called readBuff, RDBUF. And what that does is it returns a pointer to the underlying stream buff. And conveniently enough, there is an overloaded shift operator which knows what to do when it gets, as its second argument, a pointer to a stream buff. And what it does is it takes the largest chunk of that stream buff that's available and moves it to whatever its first argument is. So what this will do is it takes big pieces, in fact, the pieces according to whatever the underlying stream buff is, and moves them out very quickly. But for you, it just means that you say, take the input and shove it to the output in the best possible fashion. That's what this statement is saying. Very convenient. It makes your code smaller, and you'll have a fairly optimal situation. Okay, and we'll see the read buff. I'll show it to you several times today. Okay, now let's look at string streams. We've looked at file streams. Let's look at string streams. Nice thing about string streams is that they allow you to do in-core formatting. So in standard I/O, there's stuff to do in core formatting. String streams allow you to do the same thing, but now we have a more powerful way to do this in core formatting. Now there's a problem. If you're doing in-core formatting, who owns the memory for that? As long as you don't get a hard address, those of you who have done Windows programming and dealt with the memory there, you kind of get a feel for what I'm talking about, because if Windows wants to move that memory around, if you have a hard address to that memory and it moves it, well, there's trouble. Okay, it's the same kind of thing with string streams. You want to take a string stream and you want to start putting stuff to it. And so it'll grow, and then pretty soon it might run out of whatever memory it's allocated, and it wants to allocate a bigger chunk. Okay, great. So it does all that. But as soon as you say, well, I want the address of this character string because I want to put it out someplace or I want to mess around with it, well, it has to be frozen. The compiler can no longer do probably a realloc. It can no longer do that. Sorry, the runtime system can no longer do that. And because you asked for a hard address, so once you do that, the string is frozen. This is the way it happens. They have, it calls a function called freeze, which says, OK, we can no longer be moved. And now, at that point, you can use it as if it were simply an array of characters in memory, but you can't add any more to it because it's frozen. You can unfreeze it, which means, OK, I will give up this pointer and no longer use that hard address, and now I want to add more stuff to it. That's a function that's built into string streams. But I want to show you some of the other ways to deal with this. Okay, there are three solutions. If you call the str member function of a string stream, what you get is the physical address of that formatted memory. And the stream is frozen. If you do that, you are now responsible for deallocating that storage. So you have to call delete for that address later on. If you never do that, then the object itself will deallocate that storage. But the nice thing about this, the convenience, if you're using streams this way, with not allocating your own memory, is that you don't have to worry about the maximum length. Sounds like a good policy, especially if you're trying to make programs that you're running to other countries. They might be using wide characters. You don't want to assume anything about maximum length for any of this stuff. So this is a good approach to take. Use these the way that you can. And sometimes taking the str, using it, and then deleting it, that works just fine. However, sometimes you might want to create your own storage. So what you can do is you can create a buffer of a particular size, and then when you create your string stream, I'm creating an output string stream here, you give it, instead of, if you want it to handle the memory, you just say oster stream s, semicolon, and then it'll take care of it for you. But if you give it these two arguments, buff and the size of the buffer, then it will use your memory and it will not overwrite that buffer, including nulls and all that. It will keep it within, in this case, 80 characters. So that's convenient. You'll never exceed that buffer, and you can access it any time because you already have it. So you don't have to worry about it. When the destructor is called, it's not going to try and destroy that memory or anything. The correct thing will happen. That's how to use stack memory with string streams. But there's an even nicer way, which is once again to use the underlying stream buff. Suddenly all the storage issues and everything go away if you can use it in this particular way. If you don't have to have the physical address of the character string. And here's one situation where that works out. If I take my string stream and I simply want to send it to cout, or perhaps to another string stream or something like that, all I need to do is call the readBuff function and send it to cout. And everything's taken care of. I don't have to delete it. I never get the address of the underlying storage. It moves it efficiently as before. This is the way you should always try and do it. It also looks neater. OK, so let's look at an example. This one will copy a group of files to a specific location. So I call it gcopy for a group copy. And it uses the underlying stream buffer. The idea is you say gcopy file 1, file 2, et cetera, and then the destination directory. So you list all the files, and the last argument on the list is the destination directory where you want them to go to. So I open, OK, so I'm going to go through all of these files except for the last one, which is the destination directory. And I'm going to create an fstream object for each one. I'll just call it in. And here's the first argument, which is the name of the file. And notice that I'm using the second argument in the constructor is usually a default argument, which is just text. But now I'm inserting that default argument because I want it to be binary. If I didn't do a binary copy, it would be text, in which case text files would come across fine, but anything that wasn't a text file would get screwed up. So I open it. I make sure that it's in. I'm creating the name of the output file. First, I create an ostir stream called ofname, and then I can use all of the same operations that I do on any stream at all. This is one of the nice things about streams, is that once you learn the operations for streams, they apply regardless of whether it's a file, whether it's import formatting, whether it's standard I/O. So what I do is I'm going to construct the file name, so I get the last argument on the command line. I put a slash after it, and then I put the name of the file that I'm dealing with here. And then I have to use the end-s manipulator, and that is for string streams, and that puts the terminating null in. So that's the manipulator puts the terminating null. You've got to remember to put that in when you're doing this stuff. So from that, I create a file called out. And notice I'm calling the str function here. And so because I've done that, I'm going to have to delete it, which I do down here. OK, so I open the file. I assert that it is open. And then here's the tricky line. I just grab the underlying stream buffer from the input file and send it to the output file. This copies the whole file with that one line. Yep, no care gets and puts, just puts the whole thing out. OK, and then I have to delete this because if I hadn't gotten the underlying str, I wouldn't have had to call delete for it. But now, since I did, I am now responsible for that memory, so I have to call delete for it. So this is the kind of thing, you can quickly put together programs to do all kinds of stuff. In fact, here's another example where, one of the things that you have to do with header files is that you need to put those insulators on it. If, not, def, something, pound define something, and at the end. So to prevent multiple inclusion of header files. Well, here's a little program which automatically does it for you, first checking to make sure that you haven't done it already. So I create a base name. What I'm going to do is I'm going to construct the pound define identifier that I'm going to use as an insulator. So first I grab the argv off of the command line, stick it into my base name, and then I hunt for the dot in that base name, and I get the character pointer back from it. So I use strcare to find that. Notice I'm getting the pointer to the underlying representation here, so I'm later responsible for destroying it. OK, yeah, that's outside of this set of if braces. OK, so if I If there is no H after the dot, then the person is trying to apply insulation to an incorrect file, so I give an error message. If the dot has been found, I just set it equal to 0 to strip the extension, and then I force the name to uppercase, and now I can't add anything to it unless I decided to unfreeze it and mess around with that, but I figured this was the easier approach. Simply create another OSER stream. Send it the base name that I've messed around with, and follow that with _H_, and then again I have to put the end string on there to put the null terminator. Now I'm done with base name, so I got to remember to delete the memory. So now I have my insulator identifier. I'm ready to go on to the next step, which is I'm going to create a stir stream called hfile. And this is my header file, but it's not a file stream, it's a stir stream. I'll show you what I'm going to do here. I open the file on the command line. I open that file, make sure that it's open. What I'm going to do is I'm going to read that file into my stir stream, and of course I could do the conventional approach, which is get a line and stick the line into my H file, and I have to put an end line on it, and at the end of the file I have to remember to put the end S on it. Got to do all this stuff. Now I've tripped across this several times where I didn't remember if it put the end lines, if it put the new lines in it for me, or if I had to put them in, and often I'll forget that I need to put the terminating null at the end of this. So this has tripped me a couple of times. So instead, what's a much better approach is to simply take the input file, get the underlying stream buffer, and send it to hfile. Now, the hfile is a stir stream, so it's taking the input file and reading it in all in one line. It's putting all the new lines, and it's putting the null terminator at the end. Much easier way to do it. So in like one line, you've read the entire file into memory. Okay, and when I hit this closing brace, the in file gets closed, which is fine. The contents I've now stored inside of hfile. Now, what I can do is first hunt through the file to see if that insulator is there. So all I do is I say, I use the NCC library function, look for this string inside of a string. So inside of this string, I look for this string. And if it's there, then the insulation's already been added to this file, and so I print a message and bail out. If it isn't there, then I need to put the insulation in myself. Now, I made certain assumptions about programming style, in particular the style of the insulator and the fact that the lines at the top of the file start at the first column. The double forward slashes start at the first column. So I'm going to overwrite the old file, so I'm going to create an OF stream with the same file name. I'm going to overwrite it. And I'm going to go into this loop and hunt for the end of the comment block. So I'm looking for, in line 0 and line 1, a slash and a slash. And notice what I'm doing is pretty interesting here. Remember I said that once you learned the functions in I/O streams, they applied across all I/O streams. Well, that includes getLine. Now, getLine you usually think of as getting an input line from a file or a standard I/O. Well, it also works with a string stream. I can get a line from a string stream and stick it into this buffer. So that's a convenient thing. You know, whenever you want to do something, try it out, see if it happens. Okay, so once I get past the comments at the top of the file, I simply insert into my output file the insulator with the if not def and the pound define, etc. Well, let's see, the first non-comment line is still in buffer, and then I put the rest of the file in, line at a time. And then I put the finishing insulator. Oops, gee, anybody see what I've done wrong here? Didn't delete those. Yeah, that's the thing. It's easy to forget that, especially since the program ends and all that stuff's cleaned up anyway. So it's not really a bad thing. It's just I just now noticed that I left that out. So that's a thing that you got to remember if it's going to be important. So this is a pretty short program, but it's a way to easily go through and put in all the insulation. You can imagine a suite of programs that you can make quickly using I/O streams to handle a lot of these little problems. And of course, since you've compiled it, it's going to run a lot faster than if you were using SED or awk or one of those things. So keep I/O streams in mind when you're doing that kind of thing. Okay, now let's look at how the left shift operator works and how to write one yourself. Well, we'll look at the left shift operator. This will apply to the right shift operator. If you create a new class, it's very convenient to have your own shift operators working with I/O streams. So then somebody can take an object of your class and say, print it out, using the syntax that they've become familiar with. So what we do is we create inserters and extractors. And the inserters are the left shift operators, and the extractors are the right shift operators. Before you can understand how to create your own inserter and extractor, you need to understand the expression evaluation of, say, an expression like this. How does this work? Well, the compiler, when it sees this, parses it from left to right. With an overloaded operator, what the compiler sees is it sees an argument, sees an operator, sees another argument. So what it does is it goes and tries to find an overloaded operator shift with an argument of this type as its first argument and one of this type as its second argument. And the trick is the return value has to be a reference to an object that will fit in the remaining expression. So what the compiler does is it says, okay, here's a cout object, which is an OStream object, followed by left shift, followed by a string, char pointer. Do I have an overloaded operator left shift with its first argument an OStream reference and its second argument a char pointer? Sure enough, it does. So what it does is it rearranges this expression and makes a function call to that operator. Remember, operator overloading is just syntactic sugar. It makes a function call to that operator and with those two arguments. Now the return value to that function is another OStream. So we end up with this temp1. Okay, so what we've done is we've taken this expression and we've collapsed it into a function call. The return value is an OStream. Now we have an OStream followed by a left shift, followed by an object of whatever m is. So the compiler looks to see, do I have an overloaded function left shift that takes as its first argument an OStream and its second argument an object of type m. This is probably your new object. So it goes and it finds your class m and it sees whether such a thing exists. If it does, it makes a function call. First argument, second argument. This is the function call to the operator shift. Now the return value of that had also better be an OStream reference. So then we end up with this expression. So we have an OStream reference followed by a left shift followed by a string. So once again, it goes to look this up. When you get a really long expression, this is how it works out. When I was first learning C++ using the translator that I mentioned that took C++ code and turned it into C code, this is how I figured it out. I looked at the C code that was put out by this, and I saw a function call inside of a function call inside of a function call. And it took me a while. But I finally figured out that this is what was happening. It was simply creating a string of function calls, one inside of the other. So that is what the compiler is doing for you. Now, if you want to create your own class and create an operator shift, let's look at an example of that. So here's something I'll call vec. It has inside of it an array of integers. In the constructor, I'll initialize. Oh, I'm simply using some expression to initialize the values to interesting numbers. I could initialize them all to 0 if I wanted to, but this is just to make life a little more interesting. Okay, here is my shift operator. Now notice it is a friend function, which means that even though I'm defining it inline inside of my class, it's actually a global function because I've said it's friend. I'm just defining it inline as a convenience and also to show you what happens when you make a friend function this way. So it is not a member function. Notice that, just like what I told you, the return value for my operator left shift has to be an OStream object. If it's an operator right shift, it should probably be an iStream object of some type. but the return value has to be an OStream object. If it isn't, the compiler won't be able to evaluate it in a complicated expression because the return value has to be used in whatever's outside of it. The first argument is an OStream reference, just like I said. The second argument is a reference or an object, but a reference is generally what you'd want to use, to an object of whatever type you're dealing with here, the type that you want to extend the IOStream library to handle. In this case, my vec. Okay, so since it's a friend function, I can go inside of the vector and I can grab the particular elements inside of that and I can send them to this OS object that I've been handed. And then generally what you do once you're finished sticking stuff into the OS object is you return that object, and so it becomes your return value. So it's the same OS object that's handled all the way down this complicated OStream expression. When I do this expression, this has got to resolve to something that the compiler already understands. Well, vv.vi is an int, and the compiler knows how to take an int and put it to an OStream, so we're OK there. So somewhere, things have got to resolve to something that the compiler knows what to do with. So I've got a vector here, and now I can create a vector, and I can use this expression, and it works fine. And I can use a more complicated expression if I want. Now I want to show you how to use the underlying stream buff directly. And in this situation, we might be able to increase the speed of things a little bit. So I will create something called a byte bag. And this is just a bag of bytes, 100 bytes. And when I call the constructor, I will simply set everything to 0 using the NCC library function memset. I can dump those bytes in an intelligent way. Notice I'm using the set width manipulator here. So this is like a function call that you're able to stick inside of a stream. It says set the width to 6. You can do anything in IO streams that you can do with printf, only it's better. So now I'm going to create an extractor and an inserter. So I'm going to declare them here as friends, and same format, remember. Here's the IF stream and OF stream, the first argument, and the second argument is a reference to the object that I'm concerned with. Now, inside the extractor, the first thing I'm going to do is I'm going to take my IF stream and I'm going to get the underlying read buff. I'm going to capture the pointer. And remember, read buff returns a pointer to the stream buff. So I get that pointer, and now I'm going to call one of the member functions that are part of the stream buff class. And this is sgetIn, which says get from SB into this array this many bytes. I'm restricting this so it can only read and write to files because I'm saying IF stream instead of a generic stream. So it's getting from that file into this bag this many bytes. There's a set of functions. You can get a character. You can get a bunch of characters. There's a group of these functions that you can look up in the library manual. Similarly, I capture the stream buff pointer when I want to use the inserter, and I use sputIn. So from this bag, get this many bytes, and put it to this stream buff. So this is how you manipulate the underlying stream buff. And now we move everything in a big chunk instead of one at a time. So probably it's more efficient. I create a byte bag, and I can now read in from this file. But since I can't read from standard input because I said IF stream and OF stream, so only files. This is an example of being able to specify the use of these things. So I can read it in, I can dump it, and then send it out to some other file. Okay, as a second example, let's look at a quick and dirty tail function, which says print the last lines of this file. Okay, and we'll see that IOStreams has something equivalent to fseek in it. Pretty simple program. I open the input file, assert it. If I put the size the number of characters that I want to see at the end on the command line. Then I go ahead and capture that off the command line. Otherwise, I use this default size that I've specified up here. And all I need to do is call the seekg function off of the end by size bytes. Here's an exercise for you. Is take this program and make some modifications so that it works with lines instead of bytes. Kind of an interesting challenge. Should just take a few more lines here. And then once I get to that point, I just get the underlying stream buff and put it to cout, just like I did before. And then it prints the remainder of the file. What we're used to putting out to streams is data. Well, there's also functions that can act on a stream, like I show you set width briefly. There's end line, end string. You can make your own manipulator. Flush, for example, that's another manipulator. These are functions which act on the stream itself. They can even have arguments. So this is most of the manipulators that you have. Now what if you want to create your own? Well, the thing is, it's kind of a funny deal. Here's what a manipulator looks like. It takes as its argument an O stream, and it returns an O stream. Well, this is an output manipulator. So the idea is that you do something to that O stream, and then you return that O stream. This statement here works because the compiler finds an operator left shift that takes an O stream as its first argument and a string as its second, and that returns an O stream, so it returns the return value of this function call. Okay, but now this manipulator can be used in this expression. The thing is, so far, we have no idea how this can work, because what we're producing here is, since this is a function, if we use the function without the argument list, we produce the function address. So here is a function address in our output stream. When the compiler sees this, it must be able to go and say, well, this part here resolves to an O stream object, followed by a left shift, followed by a function address. So there must be an overloaded function that the compiler can call, which takes as its first argument an O stream object, and its second argument a function address. And yes, indeed, there is. In fact, that function address has to have this signature to it. Got to take an O stream object and return an O stream object. This special function is called an applicator. Here's the signature for it. It applies this function to your stream. So this is a pointer to a function which takes an O stream reference and returns an O stream reference. So when the compiler sees this expression, it calls this function. That's how it works. And what that function does is simply dereference this function address that your function is called, and it returns the resulting O stream. Okay. If you want to see an example of extending the O stream classes, look at the constream.h header file in the Borland class library. And you can see all this stuff done. It's fairly simple. They don't do a great deal of stuff on it, so it's pretty easy to follow. It inherits from streambuff, conbuff. It adds new functions. It redefines virtual overflow. Overflow is one of the functions in the streambuff that is called when you run out of memory. When you, say, in your string stream, if you keep putting characters in until that string stream is full, what happens when it's full is the overflow function is called. And the overflow function does whatever is necessary to allocate more memory. Well, in the constream classes, the overflow is redefined, so you can see how it works.
I/O streams are easy. In the next lesson, Bruce will cover containers and iterators. In this lesson, Bruce will use the XBAG and the string classes introduced in the workbook review chapter to show how you can build your own containers and iterators and build some useful file processing programs. While containers are not part of the C++ language, they are important classes to have and use.
As I am sure you're beginning to become aware of, containers and iterators, which we'll talk about a little later, but container classes are really essential when you're doing object-oriented programming. It seems like if they're so important, there ought to be a keyword for it. And later on, I'll show you that actually there is a keyword. At least this is my opinion, but I think it becomes pretty obvious as you see it work out, that the template keyword is really the keyword that supports containers and iterators. It can be used in a lot of situations, but that's where its real power is. So containers and iterators allow you to do safe and flexible programming because instead of just an array, you stick things into this and it makes itself bigger. It knows what you should put in it and it knows what it should get out. It can do all sorts of bounds checking and you can do lots of fancy things with it. So it allows you to add safety to your program. You can create your own containers and iterators, but it makes a lot more sense to use somebody else's library. And there are a number of libraries. Most compilers are now coming with container libraries. But you can also buy them from third parties, like RogueWave is an example. They have quite a good set of containers. What we're going to do in this section is I'm going to show you how to create your own containers and iterators. Actually, we'll be looking at the XBag again. We'll be creating a file viewer. And, well, I've been using something that comes from way back in the Borland compilers, which is More. I've been using More a lot. More shows you a file and allows you to move through it and everything. Well, what I decided to do was to create an extended More, which allows you to look at a group of files and move back and forth in that group of files. So that's kind of fun. We'll start to look at some of the problems with the void star approach. Those of you who aren't already familiar with them, we'll see even more of them where they become difficulty. And we'll look at some of the problems in the object-based hierarchy approach. So containers and iterators are not built into the core of the language, so it's possible to learn the language. In fact, it happens a lot. It happened to me. It's possible to learn the language without realizing how important containers and iterators are. They're embodied in the classes and not in their own keywords, except, as I mentioned before, template. We'll see, once I create this XBag, how easy it is to reuse it and how powerful it makes my programming. So once we get to templates in the next section, you'll see how important they are. So containers are to support the dynamic programming style that we get with new and delete. You can create objects at any time. You can create any number. You don't want to have to worry about that when you're programming. So you have a container class. It holds all these things. Of course, you can have containers that don't necessarily expand and contract by themselves, that are just used for convenience in programming. That's possible too, but I consider that a subset of the general problem. In C, we've got arrays. But compared to a container class, an array seems like an awfully primitive kind of thing. You can allocate an array on the heap. In other words, you can say, okay, I'm in my program. I figured out how many objects I'm going to have, so I will do new and allocate this array on the heap. That's a little bit better. It allows you some runtime flexibility, but it's not as good as a container class. That sort of activity should be encapsulated into a class. So we keep coming up with our XBag. So the class allows you to do things, but it doesn't specify how. It just says, give me things, and I'll take care of them, and ask for them back, and I'll give them back to you. But what is going on underneath the covers depends on the container class. It might be implemented as a linked list, or as I've been doing with the XBag, as I've just been grabbing larger and larger pieces of memory, but you could certainly use a linked list as well. And you don't have to know about that with a container class. You shouldn't be required to know that with a container class unless you want to know what the underlying implementation is. Okay, as I said before, you can create your own. It's real instructive. As a library designer, you probably should go through this process, because every time you create your own container class, you learn something new, and things become clearer to you. And when you look at somebody else's container class, not only can you evaluate it, but you have a pretty good idea of when you should use it and when you should use some other thing. As I mentioned before, buy it rather than build it in general, because let somebody else do the work for you. That's the idea with C++, is go get somebody else's code. Borland C++ has a set of containers and iterators. They have the old object-based hierarchy implementation. Don't use that. It's much more difficult to use than the template implementation. So now they have the template implementation since they came out with the template version of the compiler. Use those instead. Much easier, much less hassle. You don't have to get involved with multiple inheritance or all that stuff. So let's look at this file viewer, which I mentioned before. Looks like more, except that it views a group of files, and with the more program, you can actually look at a group of files, but you can only move forward. This allows you to move forward and backwards through the groups. And then later on, we'll add to this program so that we can search for pattern matches within a group of files. And you can actually move through the pattern matches. And this is where iterators start to come into play, because for each pattern that we match, we create an iterator, and then we just say, move to the next pattern match, move forward and backwards. So they really start to shine. Iterators, what are they? Well, if you think of a container as being analogous to a C array, an iterator is like an array index. So you've got a C array, and you say I, and you index into that array with I. Well, if you've got a container, you might want a way to look inside of that container and say this element or that element. So an iterator is like a super pointer or a super index. It's actually possible, and in fact, you can create a container so that it says, oh, well, I know where the next element is. In fact, that's when I started creating containers, that's what I did. I didn't realize this concept of iterators. And in fact, the two things being bound together can be disadvantageous, because what if you want to look at more than one place at a time? In fact, in the example that I'll be showing you, we will have a bag filled with lines, and we might want to keep track of more than one line at once, because we're going to be looking for pattern matches. And so if we want to keep track of more than one line and move back and forth, we want to just create a bunch of these iterators and have them pointing in various places. Okay, so it doesn't necessarily make sense, and in the general case, you want to abstract the concept of where I am in the container with the concept of holding a bunch of things. So you abstract the control of the container away from the containment. So that's why sometimes it's called control abstraction. And also, now we can create a bunch of these control elements. We're not trapped inside of the container. In fact, it can be more efficient than other approaches. You have to, of course, test it for your own situation. To move into this example, first I want to create an XBag with ownership. One of the issues with container classes is ownership. If you put something inside of a container class, does that container own the object? And the importance of ownership really comes when the container is destroyed. When you destroy the container, if it owns the object, that means that it should destroy the object that it's holding. This becomes a bit sticky because suppose you have a bunch of containers and you want to have, you can almost think of it as a database problem, because if you have an object and you want to put a reference to it inside of this container and that container and that container, well, now this container goes out of scope. If it takes the object with it by destroying it, then these other two containers are pointing to a destroyed object, which is bad news. So the easiest thing you can do to start with is just to say, okay, no containers will own the object. Well, the problem then is you've got to keep track, and you say, okay, this container's gone, this container's gone, this container's gone, now it's time to destroy the object. Well, if the only reference to the object is within the containers, then by the time you've destroyed the last one, you've lost any reference to the object. This is one of the places where people start griping about no garbage collection in C++, because what they would like to have is some situation where the program, the operating environment would know that nobody is pointing to this object. It's now gone, and it should be cleaned up, and the storage should be allocated for it, should be released for it. And there are certain systems like Smalltalk and versions of Lisp that have garbage collection built in, so that this issue never comes up. The problem with garbage collectors is, well, when I got started in Unix, I was using something called GNU Emacs, which some of you may have used. A wild man in Boston created, Richard Stallman. He got a MacArthur Award for it, the Genius Award. The guy's really brilliant. hard to have a conversation with. He's all over the place, but he's brilliant. Anyway, he created this thing, which was an editor that was built on top of Lisp. Well, first he built the Lisp, then he built the editor on top of it. So you could drop down and do all sorts of Lisp things to modify the code that you're using. Well, the thing is, this had a garbage collector. So you'd be writing along or doing whatever it was, and every once in a while the thing would pause, and at the bottom of the screen you'd see a little message that said, garbage collecting, done. So there would be this thing that could happen anytime. Now, garbage collection is a very convenient thing, but personally, I don't want to take C++ and say write a program for the space shuttle or something like that. It says, okay, it's now time to fire the rocket, the retro rockets or something like this. Oops, sorry, I'm garbage collecting. I can't do that. No. Okay, so this is a problem with garbage collection, is that it puts in this, this sort of wild card into your program. It's got the overhead all the time. The other issue is that most of the time you don't need garbage collection, and when you do, you know about the system that you're dealing with, and you know about the objects, and so you can set up a much smaller, more efficient system to handle your particular problem. Yes, I agree, it would be much easier to not have to think about this, but most of the time you don't. Anyway, we have to worry about ownership. So what I'm going to do is I'm going to make it an option with the XBag. I'm going to say, okay, I'll tell you whether you should destroy all the objects you contain. In fact, I'll tell you when I create you whether you own these things. And if that's the case, if I say that this bag owns everything it holds, then the destructor will go through and call delete for all the objects. Sounds like it makes a lot of sense, should work fine. So let's take a look at it. So here's my XBag again. Everything looks the same, except now I've added a new variable called owns to indicate whether it owns what it contains. And in the constructor, I have a default argument that says it doesn't own it. And if you decide to change this to 1, then the owns flag is set to 1, which means it does own it. One of the things that I'm going to do here, actually this is a new thing, because before I didn't have to zero all the memory because I wasn't going through and deleting objects. But now, if I go through and delete everything in it, if anything is not 0, then the runtime system will try and call delete for that memory. And you could be deleting anything, so that wouldn't work. So what I'm going to do here is I'm going to use memset to 0 the new memory. So the address that I'm handing memset is the address of the next memory that I've got a bigger block of memory, and next is the beginning of the new block. And so I just set all that to 0. I have a problem here because I'm dealing with void pointers. Void pointers have no type, so if I destroy a void pointer, I'll simply release the memory. The destructor won't be called. That's not what I want. So to get around this, what I'll do is I'll create a function called destroy, which must be redefined in the derived class. And destroy, I'll make a pure virtual function to ensure that somebody has to redefine this, to say how to destroy it. And what they'll do in their derived class is they'll do the necessary cleanup. Okay, now I have a function called flush, which is to flush out the whole array. And the destructor will call flush and tell it whether, and it'll pass it the owns flag. And so if we're supposed to destroy it, we call the destroy function. And then we free the memory. Okay, this system makes logical sense. Seems to work pretty well, logically anyway. But there's a snag. And the snag is, well, I didn't discover this. I thought I had a pretty good idea until something happened. And I'll show you what happened. The destructor for the XBag gets called for one which owns its objects. So flush is called. That's fine. Okay, destructor's called. Flush is called. No problem. Flush is not a virtual function, which wouldn't matter anyway because we're in a destructor, the virtual functions aren't going to be called. Okay, so it would only call the local version of flush anyway. Even if flush were a virtual function, this is the one that would be called. Okay, that's fine. Now we get down to here. We get to destroy. So that's what we want to do. Well, destroy is this virtual function that's redefined in the derived class to do the proper thing. Any idea what message I got? Pure virtual function called. Okay. Well, the problem was, even though flush itself looks like it ought to be able to call destroy fine, because destroy is redefined in the derived class, the problem is flush is being called by the destructor. And in the destructor, the virtual mechanism doesn't work. Even though we're sort of one level away, the virtual mechanism doesn't work in the destructor or anything that is called by the destructor. So we end up calling this pure virtual function. And I only discovered it at runtime when I got that message. This system doesn't work. We'll see how to fix this later. But I wanted to show you this to show you what my first approach was and why it didn't work. Now, how I will solve it for the rest of this example is I will say, oh, well, we haven't solved ownership. I just won't. I will use the default value, which says that this container class doesn't own what it holds. Let's see, we've got the size, we've got the operator brackets, all this stuff is the same. The new thing here is I've created a friend class called xbagiterator. Notice that what I'm doing here is this is a class name declaration. So I could have said class xbagiterator above it and then said friend class xbagiterator, but I'm doing it all in one fell swoop. So this says that all of the member functions of class xbagiterator, which we haven't seen yet, are friends of this current class. Now, I run into problems with the xbagiterator too. In particular, I want to be able to use a smart pointer. And we'll talk a little bit more about smart pointers later, and so you can see how they work. But I discover here that the smart pointer won't work because the smart pointer has some rules about it. It has to return an object of a class that has a smart pointer, or a pointer to an object which has whatever function you're trying to call using the smart pointer. It has to return one of those two things, and you'll notice that nowhere in that list did I mention void pointer. It has to return an object or a pointer, but they have to be typed. So I cannot return void pointer, so my scheme here isn't going to work very well. What I want to do is build a list of files from the wildcard specifications that I'm giving, because I want to be able to say emor, that's the name of the program we're developing, extended more. I want to be able to say emor star.cpp star.h. And so what I will do is inherit file list from my xbag, and I'm using the default base class constructor, which defaults to, actually I think I fixed it so it defaults to non-ownership. And here's the ownership one, which I pound to find out. So I'm not going to own these things. I'm going to get around this problem by ignoring it. So everything else is pretty standard. We redefine the getting operator. Here's destroying. So if everything were working correctly, all I'd do is I'd call delete. That looks a little suspicious too, because what happens when you delete the current object? Again, we'll ignore it. Okay, the add function. Here I'm storing, this is information particular to the Borland compiler. I get an FF block called file. I do a find first on it, and every time I find a file, I create a new str from the name of that file, and I add it to my xbag. Now notice, add is a member function of the base class xbag, but I'm inside the add function. So if I were to just simply say add, I would get a recursive function call. So I have to specify it using the name of the base class and the scope resolution operator. So I simply go through and find all the files that work with this particular wildcard. So as I go down the command line, I take the first one and expand it, and the second one and expand it. And of course, if it doesn't expand, it simply puts it in. So here's a simple test of the file list class. I've always got to test these things before I go on. I create a file list, and then I simply go through and add them all, and then I dump them. So this will expand any command line, and then you get this list of all of the expanded file names on the command line. Okay, now I want a class that holds the contents of a file. And it's going to open the file, read all the contents. For each line, it's going to create an str object. It'll be inherited from our xbag. So let's take a look. File bag. Here we go. So comes out of an xbag, and takes the name of a file and stores that file name inside of inside itself so that you can always ask it what its name is. And then it does the get line. It gets every line and it adds a new string that it creates from that line to itself. Okay, so simple enough. It just opens the file and fills itself up. And we can get any string, any line out of that file. Redefine the destroy function as I talked about before. Here's how you get the file name. And when you clean it up, all you need to do is delete the storage that you've allocated. Here it is. Allocated the storage here. I've got to delete it down here. Now that I have a way so I can expand the command line, I can read a single file into an object. Now I've got the file in an object. Now I'd like to be able to display that. And of course, I could have created a single class that opened and read a file and also displayed it. But it makes more sense to separate the functionality. You know, you might want to open and read a file and do something else with it other than display it. So I'll use inheritance and separate the functionality of the two. And I will inherit from FileBag into a class that displays the file. Then I'm going to create a collection of these FileBag objects so I can display a set of files. And the specifics of displaying are located into this file show class. So that if you, say, want to port it to another platform, you keep the things that are local to that functionality inside of a particular class. So here's how we display a file. I'm inheriting it from FileBag, but I'm inheriting it privately because I don't need people to understand anything about the underlying FileBag. They will end up using the file show. I've got some specifics here about, obviously I'm dealing with 80 columns by 25 lines. The start line says which line is going to be the top line of the screen that you're displaying. There's a message that will appear at the bottom of the screen to say, show us what file we're inside of. Okay, so there's the constructor. Here's how we display things. If there's a message, we display the message. Actually, I guess it's at the top of the screen. Do some calculations to make sure that the full screen is, in other words, when we're at the end of the file, we'll see a full screen. Various details that you have to fuss around with, implementation specifics for showing the file. Here I happen to be using the Borland calls, but of course if you're doing Windows or something like that, you'd use some other kinds of calls. And then functions to go home, to the end, to the beginning of a line, to the end of a line, down a page, up a page, all those sorts of things. So pretty straightforward. Now I want to create a container class to hold a set of these file show objects. And then I can finally create, when you tell me, show me all these files, and then I'll have an object to stick all those files into, and I can move back and forth in them. So here's a file show set. Again, I inherit from Xbag. And I'm going to, let's see, in the constructor, what we're going to do inside of add is we're going to add a new file show pointer. So we'll just keep adding it until we have, so we build a file show object, we stick it into our file show set. And pretty soon we've got a whole set of them. There's the destroy again. Show simply calls the display function for the underlying file. I've added two member functions here, next file and previous file, to move within the set of files, move back and forth. And then for each file, and you can go to the first file and the last file. And within each file, we can do the same things, up line, down line, page, down page, etc. Because I need keyboard codes, I created a little program here to automatically generate the keyboard codes for me and make an enumeration out of it. It's more of an example of I/O streams than anything else. So now I've created a bunch of tools, and I can put together this sort of remarkably small and simple program called emor. Include all the header files. I go through and to my file, the names of my files, that's my file list, I add them all. So at this point, it's expanding wildcards. So now, once I get through that for loop, I've expanded all the wildcards. Now I make my file show set, and for each name in my F list, I add a new file show from the name. So this fetches the character string representation of that name. I hand it to file show. That creates the object, reads the file in, and returns a pointer to that, which is added to my file set. Okay? Not very many lines in here, and we've accomplished a great deal. Now we show, and this defaults to the first file in the line, and we wait for user input. Up, we just send the messages. If they say control page up, we say go to the previous file, etc. And we just wait in here until they press escape. That's the end of the program. Now we can move back and forth through all kinds of files. Now I've avoided some of the problems. I've pointed them out to you and kind of said, well, I'm not going to think about them right now. But one of the problems that we have with the void star approach to this whole system, in particular with container classes, is that the compiler doesn't have any type information about a void star, so all it can do is release the memory. The proper destructors don't get called. As you can see, it gets complicated. I can come up with this destroy scheme and have a pure virtual function there, but that gets complicated too. If I don't have a pure virtual function, then the user probably will simply ignore the fact that there is this destroy function, and the right thing won't happen then either. It's gotten kind of complicated. Really what you want is a system so that the user says, I want a bag of objects. I want to put objects in and get them out. That's all I want to think about. I'm working on this program over here. I don't want to think about the details of your system. That's what we're trying to get to eventually here. Here are some of the problems that we've seen with the void star approach. It's hard to destroy the contained objects properly. In fact, I haven't shown you a working scheme yet. One thing you could do is rewrite the destructor for every class and somehow, well, it's tough. It requires for the user to understand all the details about what's going on in your underlying system. And we'd really prefer not to do that. As I mentioned before, we can't have void references. And this causes two problems immediately. One is that since we can't return a void reference, we can't have a void reference, operator brackets can't return a void reference. And that means you can't use the brackets operator as on the left side of an equal sign, which is a very convenient thing to be able to do, to look like you're assigning to an array element. You can only do that with a reference, unless you want to return a pointer and put a star next to it. The other problem is smart pointers cannot return void, as I mentioned before. And a smart pointer in particular, when you're dealing with iterators, a smart pointer is very convenient. Because it's very nice to say, take the iterator, which is pointing somewhere inside of a container, and say, oh, print, or some member of the object that the iterator is referring to inside of the container. That's a real nice thing to be able to do. But you can't do it with smart pointers. In addition, we have problems with the object-based hierarchy. Most of them have runtime type identification, which is what I mentioned to you before, allows you to do safe downcasting. It says, what type are you really, because I want to know, because I want to do something specific to you based on that knowledge. It's important in some situations, not in all situations. You don't absolutely have to have it for every situation. But when you have an object-based hierarchy, if runtime type identification is going to work, it means that in the object-based hierarchy, you're going to have, in the base class object, a member function which is probably pure that says is a or kind of, and maybe something that returns a string identifier. Some of you are nodding your heads because you're used to seeing the Borland object-based hierarchy when you have those member functions and you say, I just want to do a quick and dirty little solution, and all of a sudden you have to redefine 5 or 6 pure virtual functions which do something that doesn't have anything to do with what you're trying to accomplish. You're not using them, but you're forced to define them. So it becomes kind of awkward, and it's a bother to use because this structure has been imposed upon you by somebody putting pure virtual functions in it. And with an object-based hierarchy, as I mentioned before, you are often forced to use multiple inheritance. If you've got a container class that holds objects and you've got some other class that you want to put in here, you end up having to use multiple inheritance and redefine those pure virtual functions that they put in the object-based hierarchy, and on and on. And it becomes very difficult, and it's gotten away from what we want to do with C++, which is we who are far enough along with C++ to be able to understand how to design a class, we do all the hard bits, and then we hand it to a user who, gosh, I mean, we've just pulled them over from programming in BASIC or something like that, and they just say, make an object, send a message to the object, do simple inheritance, etc. That's what we want to be able to do, separate those two issues. So, fortunately, there's another way to handle these problems.
In the next lesson, Bruce is going to talk about something even more important than multiple inheritance, C++ templates. In previous lessons, Bruce has described the problems with multiple inheritance, void pointers, and truly reusable container classes. In this lesson, Bruce will overcome all of these problems using an important feature of the C++ language, templates.
A class template is simply a class that has one or more unspecified types. Thus, we often refer to this as a parameterized type, because there are parameters for that thing which are substituted when you create a version of this type. And the compiler is going to do that for us. The arguments in the template specify what types are the parameters that we're going to include in here. So instead of putting in a specific variable, what we're putting in is we're saying, make me an X bag to hold shoes. And that is the parameter, and the compiler is going to create this stuff for us. We will look at the template arguments. We'll look at how static members work inside of templates, because that's kind of interesting and different. I will rebuild the EMOR program using templates so we can see some of the improvements and how all the problems that we've had in the past will just go away. We'll look at creating an EMOR with multiple finds by using iterators. So what we'll do is we'll create an iterator, and so far I tried to unsuccessfully create an iterator. We'll create one successfully using templates, and we will use those iterators to point into places where we have found inside of our group of files. And that way we can move back and forth within this set of finds by simply moving back and forth within the iterators. I'll talk about some of the limitations that we have with templates. There's a couple of things that you might go try to do and discover that you can't. Probably not real soon, but I encountered these myself. We'll look at controlling what's called template instantiation. And I'll discuss that a little later. The basic idea is that if you have a template, it's more of a concept. It doesn't generate any code until you instantiate it, which is you say, OK, you have an X bag of unspecified types of objects. What I would like now is an X bag to hold shoes. Then the compiler takes your code framework and it lays it down, and it sticks shoe everywhere the unspecified type is. So it actually creates code for you. That is the process of instantiation. It's called template instantiation. And then finally, we'll look at template functions. That is, we will look at template classes, but you can also have functions which take parameters as their types. So as an example, the example I'll show you here is a quicksort, which is an obvious one because you always have to sort things, but you never know exactly what it is that you want to sort. So we can make a parameterized quicksort function so that you can just say sort apples, sort shoes, sort kittens, and it'll just do the right thing every time. And it makes life a lot easier for you as a programmer. OK. So the driving force behind templates, there's a lot of things that you can use templates for. It's not limited to container class, but the real driving force is flexible and useful container classes. So it's easy to give a container class to somebody else and have them use it for whatever they need. As I said before, you can make function templates. And what we're describing here is parameterized types, which are classes with parameters, and parameterized functions, which are functions with parameters. When we decide to instantiate this template, these parameters are specified at compile time. The compiler sees, oh, you're using an X bag with cats. So it goes and it creates a copy of your template with cats inside. That is at compile time, and the compiler does all the type checking at compile time, and it makes sure that any functions that are assumed to be called with the type that you're putting in there are actually available. For instance, inside of a template, if you're assuming that you can print things, then you're calling a print function for whatever objects you're holding. Well, if you instantiate that template with a class that doesn't have a print function, the compiler will say, oh, you can't do this. And it does that at the point of instantiation. Now, when you see this, and in fact, from the description I've given you, some of you are probably thinking, well, if all you're doing is creating this sort of macro-looking thing, and then when you instantiate it, you take whatever your type is and substitute it everywhere, that sounds like a preprocessor macro. Seems like you could do it with the preprocessor macro, and in fact, you can. And if you look at Stroop's very first book, that's what he does. He says, here's how to make parameterized types. And he shows you a way to do it with the preprocessor. And those of you who don't have access to a compiler with templates in it, this is the kind of thing that you should do. The preprocessor is kind of awkward. It's hard enough to use that people weren't doing it. And so we can kind of see the history of the way things developed. Stroop comes out with this book. He says, yes, in object-oriented programming, we do need parameterized types. Here's how you should do it with the preprocessor. And then people deluge him with requests for multiple inheritance because they don't get this other way. So he adds multiple inheritance, and then templates got added. Now, if it had happened in reverse, if templates were added first, my bet is that multiple inheritance wouldn't have been added because he would have said, hey, you can solve all your problems. Well, you can solve most of your problems using templates. So you will sometimes come across the preprocessor approach, but unless you really have to do it, don't bother. OK, so what we want to do with templates is we want to make a class using some unspecified type. And to do that, we simply precede the class declaration with the keyword template, followed by an open angle bracket and a list of arguments. And these are the unspecified types. So T is now the type that will be substituted. Now you look at the angle bracket syntax, and you might say, well, I can see some problems here if I, for instance, put two angle brackets next to each other for some reason. You can actually nest, when you're instantiating a template, you can nest these things. So you can make a bag, an X bag of X bags. We can see that later. Well, then you're going to end up with a right shift here, and the compiler's not going to like that. So you have to make sure that you put a space in between it, or else the compiler gives you an error message. It's an inconvenience, but they decided that the syntax was more important. OK, when you define a member function, you have to say the same thing, template class T, but the name of the type becomes part of the name of the class. So whenever you refer to the class, you have to say class name and give the list of the actual arguments. But other than that, it's just like defining an ordinary member function. It's just that you have to say this. Okay, that's all there is to templates. Now, everywhere inside of the class and the member functions that you see a T, when you instantiate this template, that T will be replaced by whatever the actual argument is. So here, when we define an object, suppose we have a class called type, and we have a template called class name. So we say class name type, the object identifier, and whatever argument list. So here I am defining an object called object identifier. I'm giving it its argument list in the constructor. So defining an object and the constructor argument list. And the name of that type is specified here. And at this point, the compiler sees that you are creating a new type using a template, and that is the point where it instantiates the template. And it creates all the necessary definitions for you from the template. Now, you may be wondering, well, what happens if I say X bag of cat A, and then later on, or in another file, I say xbag of cat B. So if the compiler is actually laying the code down for each one of these, is it going to create 2 copies of the code? Well, this depends on the compiler itself. Probably it will, but then the linker will come along and it's able to detect the difference between a template and an ordinary class, and if it sees multiple definitions, it will merge them. So you will only, in the end product, you will only get one definition for a particular template. So if you have an X bag of cats and you do a whole bunch of them, you'll only end up with one. If you have an X bag of cats and one of dogs, you will get 2 separate instantiations, one for cat and one for dog. Now you actually do generate more code this way. Well, how much more code? It depends. You know, the other way, there was all sorts of multiple inheritance and messing around. So it may just come out in the wash. But you are laying down code every time you instantiate a new template. The compiler's doing it for you. Okay, so let's look at a simple template. We see template class T, like I said before. So T is the parameter. Class, here's our class. So this looks like an ordinary class declaration. The only difference is the type I have, T here and T here. Okay, in this class, it's like a little array. So I have an array of these objects. And to put things in and get things out, so it's like a little container class, I use the operator brackets. This way, I'm able to put them in because I'm returning a reference to whatever I'm giving it, a reference to an object inside here. So I can put this as an L value as well as an R value to fetch things out. So the constructor, here's how the constructor is defined. Again, template class T precedes any template function. And the name of this class is not just array, but array T. So you can imagine that the compiler is probably mangling this stuff right in with it. And some information about the fact that it's a template instantiation. Everything else is the same that you'd normally see. We create a new array of T objects. And notice that this is assuming that there is a default constructor for these T objects. So if there isn't a default constructor, the compiler will give you an error message. But you can't know that here. Also, that there is an operator equals that has as its argument an int, an integral value anyway. So there's a couple of assumptions being made here. Okay, here's the operator brackets. We check to make sure if the index is within the correct realm. It returns that object as a reference, so it's actually returning an address. And then if the operator's out of bounds, I'm doing something here which is what happens when you're returning a reference and you don't have an object to return? Well, what I'm doing here is I'm saying, well, this is some sort of error, so I'm going to return star new of one of these objects. This is not particularly kosher. What you probably want to do is, well, this is what I've done here, is I've sent a message out that says, this array index is out of bounds. I'm still going to give you an object to work with. I've printed an error message, so I figure you know about this and can fix it sometime. So giving a throwaway object isn't so bad in this situation. Okay. So at this point here, when I create an array int, I give it the argument type called I, this is where the compiler instantiates the template. All the rest of the time, all it's been doing is sucking this stuff into its symbol table. It leaves it in its symbol table until you instantiate it, and then it lays the code down. Now, the thing is, when it instantiates a template, it has to have all of the definitions available. If it doesn't have the definitions available, it can't create those particular member functions. So for this reason, and also for the reason that when the compiler sees a template definition, it doesn't generate any code. It simply sucks all that information into its symbol table. For this reason, you generally, in fact, as much as possible, you put both the declaration and the definitions of a template into the header file. That's normally not something you do. Normally, you don't put function definitions into a header file. You don't ever want to do anything that allocates storage in a header file, because then if you include the header file in multiple places, you allocate multiple pieces of storage, whether they be function definitions or data definitions, and then you have clashes at link time. So normally you never do that, but with templates, it doesn't allocate any storage until wherever you use the things. So you do put it in the header file. Now I'll talk about some of the vagaries of that in a little bit. Now I've only shown you a template here with single arguments. Template can have multiple arguments. They don't have to be classes. You can use built-in types. They can have default values. For example, suppose I create a buffer and I use an integer template argument to determine the buffer size. Then, instead of using an untagged enumeration like I have before to determine the buffer size, you get an argument that you can change at compile time. It also puts, let's see, well, in this one, the entire object will be on the stack, as you'll see. So here is my class called buffer. And notice that we have what it's going to hold, and here's how big it's going to be. Now, when we create this object, the constructor is going to be called for every object in this array here. So there has to be a default constructor for object T, because we're creating an array of these objects. And whenever you create an array of objects, the default constructor has to be called. Some initialization always has to be done for any object that you introduce. OK, I've got a standard error message here that I make private. And then I create my operator brackets like I did before. OK, what's interesting here is that the argument that I'm passing to it, int size, is being used inside of the definition of this array. So it determines the size of the array. Normally, if I wanted to do this, I'd use an untagged enumeration for size. But then it would be fixed. You'd have to go into the header file or wherever and change it and recompile everything. Here with the template, I can say, oh, I want it to be 100 or 10 or whatever. And at compile time, it'll establish that. OK, so to test this, I will create a little struct called uppercase char, which contains a single lowercase char and has a constructor for it and has a print function for it. So just to make things simple. Now, here, I will instantiate a template called buff1, which holds my special char and is of size 20. Similar with buff3, and also create something called buff4, which is 100 long. Now, what's interesting about templates is that when you instantiate a template with a different argument, it becomes a different type. So once again, you can imagine that the arguments are mangled in to the name of the class. Because I cannot assign a buff1 to a buff4. Makes sense, because a buff4 is a different size than a buff1. If you think about it physically, you'd be assigning a bigger thing to a smaller thing. You don't know how to do that. Unless I went in and created an operator equals for this. If I did that took this as an argument, then I could do it. But the compiler can't create a default operator equals for you, because it'll only create a default operator equals for an object of the same type on the right-hand side as on the left-hand side. It won't create any other operator equals. So these are two different types, which makes sense, even though they have the same, sort of seem to have the same name. But they're different types because this is 100 and this is 20. And down here you can see we can assign a buff3 to a buff1 because they are of the same type. Buff1 and buff3 are the same type. Buff4 is of this type 100. This will cause a single instantiation. Both of these definitions will cause a single instantiation of this class. This one causes a separate instantiation of buffer because it's 100. In templates, you can have static members. Now, when you have a static data member inside of a base class and you inherit from that base class, you do not get a new copy of that static data member in the derived class. So any objects of the derived class share the static data storage with any objects of the base class. Sometimes this is useful, sometimes it isn't what you want. With templates, if you put a static data member inside of a template class and you create one instantiation and another instantiation, separate one, then you get two separate pieces of static data. And that could be convenient. You should know about it anyway. So let's look at an example of that. Here is a simple class that has a static data member called I, and this is the value that's going to be used for initialization. And we can set it and we can print it. When you allocate storage and initialize a static data member, if it was an ordinary piece of global storage called I, you would say int I equals initialization value. Well, I actually belongs to a class called foo. So if it's not a template, you would say int foo : I. But since it's a template, we have to give the full picture here, to basically the full class name. As I was saying before, the class name becomes not only the name of the class, but also template argument list. So we simply are defining this, and once again, we, as in all cases, we have to say template class T and the whole argument list. So this is a pretty straightforward extension of static variables inside of classes. Okay, and now I'm using the init value that I pass here as the initialization value. So inside of main, if I say create a foo, which has an initialization value of 1, and another one that has initialization value of 1. Remember, these are the same type. So since the argument lists are the same, only one template instantiation is going to occur. So we'll only have one piece of static data between these two objects. And in fact, if I print it here, I get 1. And then if I use I, the other object, to set it to 100, and I print j again, I get 100, because they're sharing the data. And similarly for this. And this is a little easier to see because it's all in one definition. But since they're both using the same template description, there's only one template instantiation. So now let's rebuild the EMOR program by recreating the XBAG as a template. This is going to solve our ownership problem right away. Then I will go ahead and actually create an iterator, which I was unable to do before because of some of the limitations that I ran into. And in particular, the smart pointer in the iterator can operate properly. So first, let's look at the XBAG as a template. So instead of having an XBAG of void pointers, straightforward enough, I put template class T at the beginning, and everywhere I had void, I replace it with T. I still want to be able to determine ownership, whether this container should destroy its objects or not. I still want to be able to do that. That works out fine. Notice add is now only going to accept objects of type T. And when it reallocs memory, it's going to cast it to a T pointer because that's what it's holding. So all this kind of follows on from what we've seen before. Now we don't have a destroy function anymore, or whatever it was that I called it before. Inside of flush, I say, if you're supposed to destroy it, delete the object in the array. And that, we assume, will be a virtual destructor. So the proper thing will happen. Or it doesn't even have to be a virtual destructor. If you're just putting in objects, it's going to be delete an object of type T. So the type information is there. The proper destruction is going to happen. So everything is going to work well. Let's see, what else do we have here? Everything else is pretty much the same, except now we're able to return, whereas before we could not return a void reference. Now we can return a reference to an actual object type, and we can use this operator in a much more convenient fashion. We're not getting a pointer back, we're getting a reference. Here is my iterator. And since the iterator also has to deal with objects of a particular type, it too is a template. And this is how we declare it. We're using a class name declaration, and I have to give it a template argument list using the template arguments that we have here. Here is the iterator that we're looking for, that we're going to create. Inside of it, it contains a reference to an XBAG of type T that holds T's. So we get a reference, and here's how we initialize it. And from then on, we can treat it like it's our own particular XBAG. And we can return elements from it. We can go to the top, to the end. The iterator, remember, is sort of like a super pointer. This moves it to the top or the end. We can ask how big the bag is that we're pointing to. We can increment it by overloading the operator plus plus. This is the prefix version of the operator plus plus. In other words, when the plus plus happens before the iterator. The postfix is when the operator plus plus happens after the iterator. And notice that I'm doing, well, actually, I'm doing pretty much this. No, I'm doing different things. If it's the prefix, I increment the index before I return the value. If it's the postfix, I get the value, and then I increment the index. So they do actually do different things between the prefix and postfix. There's also an operator minus minus for this iterator. A lot of times you'll find that the iterator moves back and forth. You can assign it to something, and then you want to increment it or decrement it, so it moves back and forth. Oh, I was wondering what happened to that. Here is the smart pointer. And what this is going to do is it's going to return the pointer at a particular location, which, as you'll see a little later, can be used to select a function for the t object that we're holding. So this is quite handy because you have an iterator, and you say iterator arrow print, even though I don't have a print function inside of this iterator. What you end up getting is this, the iterator smart pointer returns a pointer to the object that's held inside of the container, and that object had better have a print function, and the compiler checks to make sure it has a print function. And that is the print function that gets called. So the compiler actually does sort of a double dereference for you, but it gives you very convenient syntax. Once again, operator overloading, syntactic sugar. That's what it is. But it's nice syntactic sugar. I'm going to create the file list, this time from an X bag of strings. So I didn't have to do any special inheritance for that. Just say, make me an X bag of strings. So in this line, the compiler sees that I need an X bag to hold STRs, and it instantiates it for me, and then inherits from that, all in one line. You can do some pretty effective, fast programming when you have templates. Then the add function is the same as we saw before, the dump function, and then xbag has the operator brackets so we can fetch things out of it. So file list has gotten smaller. Here's the file bag, again inherited from xbag, which holds SDRs. And next is the file show, which is inherited from the file bag. Remember, the bag holds the file. The file show is a file bag which can display itself. And the file show set, this time it's inherited from an xbag which holds file shows. Once again, I just create it using the template instantiation right in the inheritance list. The rest of the code is the same. So when I do the emor with the templates, it really doesn't look any different. It's all the same. So the templates, what they've provided us with is a nicer, cleaner way to program, plus everything is getting destroyed properly, where it was not before. So now I have a better, from a programming standpoint, I have a better version of emor. Now what I'd like to do is I would like to create this emor so that I can find more than one string and do it dynamically. So what I will do is I'll first display the list of files, and you can move back and forth in them. And then if you want to do a find, you can press the / key and type the string that you're looking for, and it'll quickly go through and look through the entire set of files, because they're all in memory now. Look through the entire set, and every time it does a match, it will create an iterator and point it to the place where it matches. And then it'll end up with a list of those iterators, and we'll be able to move through that list. And the iterators themselves will be the things that handle the display. So I'm going to move the display capabilities away from the container class, where it is now, into the iterators. I will now create my file bag iterator. Notice the iterator now concerns itself with the top line on the screen. There's going to be a line that it will highlight. That's the line where it's done the find. There's a message buffer where it'll show you what file it's in, and then the screen size, that kind of specific thing. Now notice that I have created this iterator using composition. So I've composed it with a reference to a file bag and some ints. And here in the copy constructor, what I've done is, so I'm making a file bag iterator from an existing file bag iterator. I've gone through and picked off all the pieces and done essentially assignment to all the internal members. Now the reason that I've commented this out is because I don't have to do this. I can just let the compiler build the copy constructor for me. And what it'll do is it'll do assignment for all of these things. So it's an option. You know, if you want to take it over, you can. But here's a situation where I didn't need a copy constructor. OK, the iterator's got the operator plus, and it's got a display function. OK, so the display is all taking place here. And as we go down, we can see functions that I showed you before, home, end, upline, up page, etc., all which have been moved to the iterator instead of the container. So in effect, I'm doing control abstraction here because I'm abstracting the control into the iterator instead of the container class where I had it before. Now the iterators themselves, you can say, you display yourself. And it knows how to do the right thing. It's much easier than having it in the container. So now, once we've done that, we can create an emor with iterators. The string buff is simply a place to hold a message. And notice it's just a character buffer with a constructor, a automatic type conversion operator. So anytime you use a string buff, it's really essentially the string that we had before. The difference is there's a function called setMessage so that we can format a message. Notice I'm using an oster stream object so that I can use the formatting capabilities here. So it formats that in, and it goes directly into the buff inside of this string buff. So that's a convenient way to format a message into it. What I've created here is a function. Now I've got a function called showSet that takes as an argument an X bag of file bags. This is an X bag that holds a file bag. So it's a collection of file bags. So this is our whole set of files that we're going to display, and I call it fset. And then the find string, which I use a default argument of an empty string. If it's an empty string, it'll simply display the whole file with no highlights. But if you put a string in other words, if you do a showSet call with a set of files and a find string, then it'll go through and make a bunch of iterators for that and highlight those lines where it's found. OK, so I make an X bag to fill with file bag iterators called itset. So here's where, if I have any finds, I'm going to put them in here. Well, actually, if I just have a set of files, I'll put a single iterator in for each file. What this expression says, if not star find string, that means if find string is pointing to 0, which means you got a null terminator at the beginning, which means this is what has been passed in, then this is just an ordinary display of all the files. And so what we're going to do is, for each file in the fset, we're using the brackets operator to pick out the file, make a file bag iterator for that one, and put our default message on it. And so stick that in. And then when we display it, we're simply displaying the file itself. If that is not true, if there is a find string, a non-null find string, then we're going to create a set of matches to our search pattern. So we'll go through the entire set of files. And for each one, we start by creating a file bag iterator. And we give it the argument of the current file that we're interested in. And then we compare the find string to our current file bag iterator object. Now what happens here is, OK, this is a pointer to it. When I dereference the pointer, I get an object, a file bag iterator object. It's used in an expression which is expecting a character pointer here in the first location. So the automatic type conversion operator is automatically called to produce a character pointer out of that. So then this function can now compare this string with the string that's produced here. If it finds it, it calls the highlight member function to highlight that line. And it adds it to the iterator set and creates a new file bag iterator from the existing one, because the existing one is pointing somewhere down into the file. So it creates a new file bag iterator from that one, so the new one is pointing at the same place the old one is pointing at. So now we're only searching forward in that particular file. We don't start from the beginning. And then we use the pre-increment plus plus operator to move that on to the next line, because we already matched the current line. So we want to move it to the next line and then go back to the top and see if we found the next string. Now, if we didn't, then this last file bag iterator that we created should be destroyed here because we're not using it. Okay? And we're looping through all the files in the bag, and for each file, we're hunting through for each find that we can locate and creating a new file bag iterator and sticking it into the it set here. So now, at this point here, we've got an it set filled with these file bag iterators that correspond to all the matches. So we're done with the searches, and so we go into this while loop. We display it. We get a key and match it to whether it's up, down, page up, page down, using that enums that I created earlier in the day, and simply call these member functions for that particular iterator. So what this does is it selects out of it set, it selects the particular iterator, and then this calls the member function for that iterator. So that's fine. Okay. Now, if you press the / key, that means you want to do a search, clears the screen, asks you for a pattern, and it calls show set again with the file set that you're currently dealing with and whatever the string is. So we're doing a recursive call to show set. So it goes down one level, and within this set, it finds another set. So when you back out, you're back in the current set. When you back all the way out, then you quit. So here's the quit from the current function. So inside of main, all we have to do, it's remarkably small again, is we grab all the command line arguments and expand them. We create an X bag, which holds file bags called fset. And then we add, for each command line argument, we add a new file bag. And once we're done that, we have our basic set, and we call the show set function. Now, there's some limitations on templates. One of the limitations that I've run into, something that I wanted to do, was that inside of a class, I can't say friend something that's another template. So if I have two templates inside of one of the classes, I can't declare the other template class. And that's kind of a problem. That in this class called bytebag to use templates. So what I want to be able to do is say, I would like to determine the size at compile time. And notice it has a default argument. You can have default arguments in templates as long as there are built-in types. So my bag now takes this argument and uses it to determine the size of this byte bag. And that argument's used everywhere else. Notice I'm not even using any classes here, but it's still a convenient, useful thing to do. So I can dump it, and down here, this all works fine. I can have my IF stream and OF stream right shift and left shift operations. That all works fine. Now, inline nested templates are all right if you define them inside of the class. If you try and declare them in the class and define them outside of the class, the best answer I've been able to get from the compiler writers for this is that the behavior is explicitly undefined. That is, the standard has not specified exactly what's going on here. The idea is that they're restricting this. When I show you the example that doesn't work, I hope you'll understand it a little better. They're restricting this because it's a little safer. You could allow this behavior, but until we know more about what kind of can of worms it opens up, it's much safer to be restrictive, and later we can open it up. So the following example won't work. So it's the same byte bag that I showed you before, except notice what I'm doing here is I'm saying the argument I want to take to this is a template argument. And down here I'm defining this. The language won't allow this right now, because we're inside of a template and we're referring to some other template inside of this template, if you define this function inline, it works okay. But if you define it out of line, that's what I did before. I defined it inline, and I didn't have to have this argument here. But if you define it out of line like this, you can't seem to get it to work. So that's something to be aware of. There are certain limitations. Okay. I've talked a little bit about template instantiation. That is the point at which the compiler lays down the definition for this template. Now, obviously, I'm giving you as many of the details as I can. Most of the time, you don't have to worry about a lot of the stuff that I'm showing you. I'm showing you the edges. Most of the time, templates just work right, and they're very easy to use. But sometimes you run into some issues and situations that I'm trying to show you here. When a template is instantiated, the compiler must have all of the functions available. What you should almost always do is put all of the definitions for your template functions inside of the header file. If you do that, everything will work okay. But for some reason, you may need or want to separate the interface, which is the class declaration, from the implementation, which is the definition of the member functions. You might want to do the usual thing of putting the header file, having the class declaration, the header file, and the definitions in a CPP file. Okay, you can do that. It brings up some problem issues because it puts the compiler in a quandary. Suppose we have the declaration up here, but no function definitions. And so we want to put the template function definitions in a definition file down here. We have to include the header file, of course. And we put the template definitions in here. Seems fine so far. Problem is, over here in main, we include the header file. And we go ahead and use the template to instantiate some classes here. And the compiler doesn't have all of the definitions from the header file because they're over here. So here you don't know that these templates are being instantiated. And over here, you don't know what the definitions are to instantiate the templates. Once again, it makes much more sense to put these into the header file. However, there's still a way to handle it if you really have to do this. In the ideal case, the compiler just knows what it's supposed to do. It says, I see over in main there are template instantiations for this type and that type. And I will therefore make these template instantiations. Well, how does it do this? It's a tricky problem. The AT&T compiler, I understand, what it does is it doesn't generate any templates unless they're explicitly instantiated and it has all the definitions. And in fact, it might not even do it then. I haven't seen it work myself. This is what I'm told. It goes through to the link phase, and then when the linker discovers that a template is used that hasn't been instantiated, what it will do is it'll restart the compiler, giving the compiler that information to instantiate this template. So you might go through this several times before all the proper templates are instantiated. But that's one way to do it. Some compilers make you responsible for telling it what templates you're going to instantiate. And again, the nicest solution is to put them all into the header file. But the Borland solution is to make you responsible. That's completely legit. That's part of the ANSI spec, says that the compiler can require that the user tell it somehow. So if you have to separate the interface from the implementation, what you can do is use some pragmas that the Borland compiler provides for you. And the -JG pragma is the default. It says whenever an object is used that requires a template to be instantiated, instantiate it at that point and merge multiple definitions at link time. That's fine. If you don't want to merge multiple definitions, this is the important one. It says, if this flag is on, it says don't generate multiple definitions, but instead simply make external references. So say that it's out there somewhere else. So in this situation, you have to use an extra trick to tell the compiler to generate the definitions, and you have to do this in the template definition file where all the template member functions are available. You don't want to create any instances in this file because the uses of them are, the instances are created somewhere else. So to do this, you create a type def with the template signature that you're trying to create, and then some dummy name here. And the compiler, when it sees this, it'll instantiate the template, but it will not create any objects of that template, because this is just a type def. The compiler sees it. It goes, oh, you're going to use it someplace. I'll create it here. So what we end up doing is you have the header file, you have the declaration of the template, not the definition, and then use pragma option -JGX. So it says, from now on, only create external references to any objects of this template. Inside of the implementation file, we define the template, and then we go back to automatic template instantiation, and we put these type defs in, which we happen to know that we need because we're using them over here in main. So you put the type defs in, the compiler sees it, and it instantiates the template. Inside of main, at this point, the automatic instantiation is still turned off, so all it does with these two things is it generates external references. Now, of course, this is kind of awkward and funky because every time you instantiate a new type of template here, you have to go back here and make changes. It doesn't make much sense, but this is how you would do it if you really have to have the definition separated. Again, put it in the header file. Well, I'll show you one situation where it is important to be able to use these pragmas. Template functions. So far, we've only looked at template classes, whereas a template class allows you to define a family of classes. It's a family because there's an unspecified type, and it means that you can create a basket of apples and a basket of oranges and a basket of pears. So you've got a family that is defined by that single template. A function template allows you to define a family of functions. So in the example I'll show you here, you have a quick sort, but it's really a family of quick sorts. It's a quick sort for apples and oranges, etc. The syntax is identical to what you would expect. Okay, I'm going to create 3 template functions here. The first one's very simple. It's just the swap. All I'm going to do is swap an object called A with one called B, and both of these are of type T. And notice that it's just a function with some type in here, and I precede it with template class T. So it's exactly like a class is. Now, when I do this expression, I'm assuming that there is a copy constructor or that the compiler can create one for you. The only time the compiler couldn't create one for you is if one of the constructors has already been defined explicitly by the creator of that class and the copy constructor has not been defined. Then the compiler won't create it for you. Here, we assume that there is an operator equal defined for objects of type T. So we go through the swap. Swap is something you almost always have to have with a sort. Here is where the sort takes place. Fairly short function. Notice that I call it not quicksort, but quicksort underscore. And I'll tell you why in a minute. But this is a typical quicksort. We have the array, we have the right bound, we have the left bound. It goes through and does a comparison. Notice I've set it up so that it only needs an operator less than, but it does need an operator less than. So the objects have to be able to be compared. And if they're not, when you try and do a quick sort, the compiler will give you an error message that says there's no operator less than for this. And then it calls the swap function. So the quick sort underscore is what is responsible for instantiating the swap function. And just like an ordinary quick sort, it breaks it up into regions and does a recursive call. This works fine if you're sorting objects that have greater than, less than, that sort of thing. That where the syntax is what you expect for comparison. However, there are certain situations where greater than and less than don't do what you want. And in particular, in this situation, what happens if we try and sort an array of care pointers? This function will sort that array into ascending pointer order, not ascending string order, right? Okay, this is not doing what we want it to do. This is a problem. Fortunately, all we have to do is say, oh, I have this other version of quicksort over here, same signature. I want you to use it instead. So what I need to do is I need to declare that in the header file so that the compiler knows that there's this version, and it should call it, and it shouldn't instantiate the template for an array of char strings. Now, what happens when I do this? Okay, it's just a declaration. So I say, I'm making a declaration here, just information to the compiler that I'm going to use this function. The compiler sees this and it goes, oh, I see you're going to use this function. I will instantiate the template to comply with this function so that you've got a quicksort to handle char stars. Well, that's precisely what I was trying to get away from. I don't want it to instantiate a quicksort for char stars. I want to define that function myself. So here's a situation where I need to turn off automatic template instantiation. So I use this pragma -jgx. I say turn off automatic template instantiation. Then I can declare this function without getting a template instantiated for it, and I can define it in some other place. Okay, so I've done that. We'll look at the definition in a minute. Now I want to turn automatic template instantiation back on so that the function will be created for me for all the other cases. Okay, now I had the quicksort underscore. Well, I've never liked the syntax that you have to use to call a quicksort. My preference for calling any sort of a sort routine is hand it the array, and if you absolutely have to, which you do in this case, hand it the size. Okay, but that's what I want to do. Give it an array and how big the array is and sort it. Well, with a quicksort, you have to hand it the array and the one boundary and the other boundary. So what I've done is I've simply made a final wrapper for the first call, and it takes my arguments and it turns it into the appropriate call to quicksort underscore. So it makes it more convenient. Okay, we have to define the char star version of quicksort. After including the header file, here is the definition for quicksort underscore for the char star version. And notice that instead of using greater than and less than, I'm using string compare. And we can test the quicksort. Well, this is just some various kinds of testing you can do, but you can see the function call to quicksort. Oh, here's one of them. So at this point, when the compiler sees that you're going to use it with an array of characters, it instantiates one to hold an array of characters. Here's our special version being called for an array of strings. So once you have this quicksort defined, it's very easy for people to use it. They don't have to think much about the details of setting it up or doing it right, which you always had to do with ordinary sorts.
As you've seen, templates are indispensable. They're the key to object reusability. Now stay tuned for Lesson 6, where we'll cover special member functions. In this lesson, Bruce will tell you about several C++ features we've collected under the heading Special Member Functions. You probably think you can't combine apples and oranges. Well, with C++, you can.
First, we'll look at overloading new and delete and changing the new handler. The new handler is the function that is called when you run out of memory, calling new. You can overload new and delete on a global basis or a class-by-class basis. We'll look at those. We'll look at the so-called smart pointer, the operator arrow, which I showed you briefly a little earlier here. Look at automatic type conversion, some of the problems and pitfalls with automatic type conversion, how you do it. Pointers to members, what a pointer to member is and how it works. Briefly discuss the function call operator, which is something that you should at least know about in case you get into a situation where you want to use that particular syntax. And discuss when we use member operators versus friend operators, what the advantages and disadvantages of those are. So when we overload new and delete, you can do it for several reasons, but most often you're doing it because you want to do your own storage allocation. Thing to remember about new and delete is that, well, in particular with new, when you overload operator new, this doesn't have anything to do with the constructor. When the user calls new to create an object, the compiler says, Okay, first I need to call operator new. Then I need to call the constructor for the memory that's returned from that. So it's a subtle difference. The user is calling new to create a new object. The compiler does two different things. The compiler still maintains rock-solid control of the fact that it calls the constructor. But you can do the storage allocation to get the memory before the constructor is called. So of course you had better provide the correct amount of storage. There's various reasons that you want to do this. Speed is often the case that you want to do your own storage allocation. Sometimes you want to put them in a particular location. I gave a brief description of that earlier. When you want to use new to specify a location, put it in a fixed place in memory. If you overload new and delete on a global basis, that means that everybody who calls new will call your version of new. So when you do that, you can't call the original versions. You've taken over. But you can also overload new and delete on a class-by-class basis. That means that if you say, okay, inside of a class, I'm going to create an operator new, that means so your class is called foo. If I say new foo, that means that for the storage allocation for that class, that operator new is going to be called. But if I say new bar for some other class, and it doesn't have an operator new or it has its own, then that operator new will be called. So when you overload operator new on a class-by-class basis, you're only changing the storage allocation when an object of that class is created using new. So it's much more focused. And generally, it's what you want to do, unless you want to somehow change the behavior of new and delete on a global basis. Okay, what happens when new runs out of storage? Again, this is different from when the constructor fails. This is a much easier problem to solve than when the constructor fails. We'll be talking about that sort of failure later in exception handling. But when new fails, the first half allocates storage. Later, call the constructor. But when new fails, what happens? The runtime system calls a special function called the new handler. The new handler is what is to be called when you run out of storage, and you can change the new handler with a function called setNewHandler. You hand it the address of the function that you want to replace the current new handler with, and it actually returns the address of the previous new handler. So you can stash it someplace and restore it if you want to. That way, you can establish what happens when you run out of memory. Let's take a look at an example. So this is like a little toy garbage collector. I'm going to create a class called garbage, and it's going to occupy 1K for each object. So I'm going to create, each one of them is going to occupy this much storage. The argument to operator new is the size of the object, and that is handed to you, that's determined by the compiler and handed to you by the compiler. So the compiler knows how big the object is, and it hands it to your operator new. And you have to return a void pointer from that. Operator delete takes a void pointer and deallocates the storage. Remember, the destructor is the thing that handles the cleanup, and then the operator delete is called to release the storage. So by the time the thing is cleaned up, it's no longer an object, it's just a chunk of memory. So that's why you're handing it a void pointer. Now, if you do overloading of operator new and delete on a global basis, you use the same signatures. And these are in a header file called new.h, or they should be. Okay, so this is my garbage object, and I'm going to create something called a mem table, which is simply an XBag of garbage objects, or actually pointers to garbage objects. So once again, the XBag template comes right in handy. All I have to do is, this is how quick it is to create these things. Okay, my operator new needs to allocate the correct amount of storage, which we know, since the compiler gave it to us, is the SZ argument. So I'm going to call the global version of operator new by using the global scope resolution operator, double colon with no class name in front of it. So I call the global version of operator new, and I allocate enough storage for it. And before I return the address of that storage to be acted upon by the constructor, I add the address to my mem table. So now I've stored the address of this object in my mem table, later on I can mess around with it. And this is one of the nice things about using operator new in this situation, is you can store this away. So I'm making myself a little garbage collector here. Delete is called after the destructor is called, so we get the address of this object. And what I'm going to do inside of my operator delete is I'm going to put out a little tilde to indicate that this object has been deleted, so I can kind of track it on screen. And then I go ahead and call the global delete function. So now my garbage collector, which is what I'm going to install as the new handler, all the garbage collector does is, remember I talked about garbage collecting done, so it's doing the same kind of thing that I used to see on my screen with GNU Emacs. So it prints out the number of items, because remember this is an XBAG, and XBAG has a member function called size. So it prints out the number of items, and then it calls the flush function for that mem table with 1, meaning that it should destroy the objects that it's flushing. So that goes through and it frees up all that storage. So inside of main, first thing I do is I call set new handler to replace the existing new handler with my garbage collector. Now the signature has to follow a specific form, which is it takes no arguments and it has a void return value. So once I set the new handler, now I'm just going to go into this infinite while loop, throwing away the return pointers to the garbage objects that I've collected. But I know that the operator new for garbage is storing those in the mem table. So it goes through and it does this until I run out of memory. And at that point, the new handler gets called, and the new handler calls the flush function for that mem table and frees up all those objects one at a time. Now what happens after the new handler is called is that it comes back and you get another shot at trying to new that object. So this will just continue doing this, continue garbage collecting and releasing the storage, and then going back into this while loop. So, like I say, it's sort of a little toy garbage collector. Okay. Next, smart pointers. This is the overloaded operator arrow, and it acts differently even for an operator. I mean, we're used to thinking that an operator, when a compiler sees A plus B, it's going to turn it into a function operator plus A comma B. So it does a little mixing around of the arguments, but that's pretty straightforward. With an operator arrow, all sorts of very interesting things can happen, and this next example should be kind of an interesting mental puzzle for you to follow through. Okay, the thing about operator arrow is that the compiler performs several levels of indirection for you. And I've shown you how it works in an iterator, because that's the place where you'll find it most syntactically useful. Okay, the rule for smart pointers is that a smart pointer has to return either an object, or a reference to an object, because that's effectively the same thing, of a class that has its own smart pointer, which will then be dereferenced, quote unquote dereferenced, but it's actually dereferenced by the compiler at compile time. So it must return either an object or a reference of an object with a smart pointer, or eventually you have to get to the point where one of these things returns a pointer to an object. That object has to have the function that you're eventually trying to call. So here, if you have an iterator I to a bag of objects with a print function, okay, the objects in the bags are the ones that have the print function, not the iterator itself. But we're able to do something like, if you define the operator arrow correctly, you're able to say I arrow print. So that's the idea of the smart pointer. It does one or more levels of indirection. So let's take a look at this little puzzle. So start simple enough with a struct called Bob, and it has a pure virtual function called foo. Ralph is inherited from Bob, and it redefines foo to print something out here. Next, we start with a struct called Fred, and Fred has an operator arrow defined as a pure virtual function. Fred's operator arrow returns a Bob. Next, Joe is inherited from Fred, And it redefines the operator arrow to return a new Ralph, which is an object of this type. And so it returns a new Ralph as a Bob pointer, so it's doing an upcast as it returns that. Okay, hold all of this in your mind now. Next, we'll create another hierarchy. We've got base, and we have another operator arrow which returns a reference to a Fred object, another pure virtual function. Derived is inherited from base, and it redefines this operator arrow to return a star new Joe, because the reference has to have an object to deal with. And Joe is inherited from Fred, so yes, that's correct. That can be a Fred reference. So again, it's doing an upcasting. Now we'll have a class called holder. And holder holds a base pointer, and we hand holder a base pointer which it stashes away. I wanted to set it up something so I could do several levels of indirection with the operator arrow. So holder has an operator arrow which returns a base reference. And now finally we can get to main, and there's not much code here, but we'll see what happens. So we create a holder, and in it we stick a new derived object. Now we say h arrow foo. Okay, obviously there is no foo function for a holder. So the smart pointer is in operation here. So we got to trace this through and see what happens. So we start with an h, we call it smart pointer, and its smart pointer returns a base reference. So we'll have to go back and look at base. And a base object also has a smart pointer which returns a Fred reference. And Fred also has a smart pointer which returns a Bob pointer. And Bob finally has a function foo. Now the compiler does all this dereferencing. Well, it's not really dereferencing. It's actually just making a series of function calls. Syntactically, it seems like it's dereferencing it. But it does all this dereferencing at compile time. So it does type checking and everything. It makes sure that you're not doing something completely out of whack. So it makes sure that wherever you end up really does have a foo function. But in addition, I've done a bunch of virtual function calls here just to make sure that the virtual mechanism doesn't get messed up by the smart pointers. And in fact, it doesn't. We end up with the correct function being called. There are no problems here. So this expression is evaluated to a bunch of successive function calls. It gets much bigger, but it's convenient sometimes because the syntax looks nice. Well, most of the time the syntax looks nice using iterators. A lot of the features that were added to the language, like templates and smart pointers, were really intended to support containers and iterators. It's interesting because I don't find this a lot in the literature. Not a lot of people say, oh, by the way, we're doing this so that you can use containers and iterators. It's almost as if they don't want to admit that or they don't want to say that. But the more I work with it, the more I see, yeah, that's what it's most useful. Of course, it's orthogonal and it works in all situations. But really what you're trying to use these for is containers and iterators primarily. Of course, I may not have seen the examples yet where they're useful in a lot of other cases. Okay, next, automatic type conversion. With a built-in type, you know that it can be converted from an int to a float or a char to an int. All this kind of stuff can happen. The compiler sees an int being used where it expects a float, and it will convert it automatically. Well, when we create a user-defined type, we always like it to be able to do all the stuff that a built-in type can do, like, for instance, pass by value. That's what the copy constructor is for. So with a user-defined type, we can do the same thing. There's two ways to do automatic type conversion. What we're doing with automatic type conversion is we're saying, here, compiler, here is a way to take an existing type and convert it into a new type whenever you want to. So if you've got an apple and you want to convert it to an orange because an apple's being called inside of a function which is expecting an orange argument, you can do it. You can quietly do it. There's two ways to do it. One of them is, as you've seen earlier, you can overload the operator and then you put the type name that you want to turn it into. Like, for example, in the str function, or str class, there is an operator char star. Notice this is an operator that has no return value because the return value is the name of the operator itself. So this is where if you have an orange and you want to be able to turn it into an apple, you say operator apple, open close paren. Okay, that's an automatic type conversion operator to go from the object you have to another type of object. There's also a way to go to the destination. And in the destination, you can convert from whatever the source is. You do this by creating a constructor which takes as its single argument, can only take one argument, an object of the source type. So you would say, if you want to convert an orange to an apple, inside of the apple class, you would have a constructor apple, open paren, orange, close paren, or a reference to an orange. Okay. In either of these cases, if either of these things exists, the compiler knows that it can call these functions to quietly do an automatic type conversion. Now, the problem with automatic type conversion, it can be very useful. You should know about it. There's situations that I've been in where I've had to redefine a whole bunch of functions so that they would handle my new type. And then suddenly I realized, no, all I have to do is a single automatic type conversion, and I can eliminate all these function redefinitions. So it can be very useful. It can also introduce ambiguity. What if two types own the conversion from one place to another? What if orange has an automatic type conversion operator to apple, and apple has an automatic type conversion operator, which is its constructor, from orange? Well, if you have two ways to get from one point to another, the compiler doesn't know. It's an ambiguity, and it throws up its hands, and it's in trouble. So it gives you an error message. The thing about this is you know when you create the class when you have such an ambiguity. Therefore, that's a much simpler problem to deal with. The real problem occurs when you have multiple conversions from a single type. And this is often what we refer to as fan out, because you have a single type, you have an apple, you can convert it into an orange, and you can convert it into an apricot. Generally, you want to avoid fan out as much as possible, because that causes possible ambiguities, which we'll look at in this next example. Okay, so here's several pitfalls with automatic type conversion. I have a struct A, and here is an operator B, which says, here's how we make a B from an A. Once again, no return type because the name of the operator is the return type. So we've got a struct B. Now we can make a B from an A again by a constructor which takes as its single argument an object of type A. Okay, so we have two ways to get from A to B. And if we create a function which takes a B and we hand it an A object, which of those conversions is the compiler supposed to use? It doesn't know. It gives you an ambiguity error message. That's pretty simple to see and fix. Now, what's a little more problematic is if you have an ambiguous type structure. So suppose we have a struct X and Y and one called Z where we have fan out occurring. We can convert a Z into an X and into a Y. If we have an overloaded function which takes an X and a Y and we hand it a Z, which conversion is it going to use? Is it supposed to convert itself into an X or a Y? Well, it's ambiguous. It doesn't know what to do. Now, what happens if we start out with the struct U and one V, and we have a way to convert from U to V using the constructor for automatic type conversion? Now we have a function which takes a V argument, and we have another function here called test3. If we hand it a U object, the compiler goes up and it says, okay, you got a U object, you want to convert it to a V, I'll call this function here, and everything's okay. That's fine. But now what happens later on, if I add a struct W and it has a way to convert from U to W, and I define another function, overloaded function H, which takes a W as an argument. Now, if I do that, the above code suddenly breaks because it doesn't know whether to convert the U into a V or to a W. So this is a situation where later addition of new types and functions causes the problem. Well, be careful is the key word here. Only use automatic. It's like operator overloading, all these features. Only use them if you really understand them well enough to know that this is what you need in this situation. This is really going to give you an advantage, and you can restrict the use so stuff like this doesn't happen. Pointers to members. Pointers to members are kind of weird. In C, there is a macro called offset of. If you have a struct and you say, what is the offset of this member into this struct, it will give you a number that says how many bytes that offset is. Okay, that concept is pretty straightforward when you have a struct with just data members. But what if you have a struct with function members and you want to select one of these function members at runtime? Well, with offset of, you can select a member at runtime. It's pretty easy. This is really kind of a pointer idea. You have the pointer to the start of the struct. You know the offset. You know where that element lives in that struct. But the thing about pointers is they have to have a specific address. And what if we wanted to get the address of a class member? Well, you'd really want the offset of it, but if it's a function, you sort of want the address of that function, but you can only call that function when you have an address to pass the this pointer to as its first argument. So it's kind of convoluted. So a pointer to a member says, okay, I'll give you something that looks like an address. Say it looks like a function pointer, but it's specifically for this particular class. It's kind of like a pointer. It's kind of like an offset. You can't use it. It doesn't become live until you dereference it with an object. So you can't just, it's not like a pointer where you can just dereference a pointer. It's pointing to something absolute. This you have to say, okay, this is a pointer to member. It's an offset into this object. Here is the object that it's an offset into. Now dereference it. Okay, a definition of a pointer to member is a pretty straightforward extension of the definition of a pointer. So if you want to define a pointer, you would just say int star foo. If you want to define a pointer to an integer inside of a class, you simply put the class name and the scope resolution operator in front of the star foo. Okay, with dereferencing, however, you have to have an object of the right type, and the compiler checks this. And you must be selecting a member of the right type. You can't take a pointer to a member that is a pointer to an int and point it to, say, a function address. It has to be the correct type. Type checking is performed on pointers to members. If we've got an object, we say f dot star foo. If we have a pointer to an object, we say fp arrow star foo. So we've got to have that object before we can dereference this thing. Now, pointers to members are a little strange. Where do you use them? The most useful thing that I found for pointers to members is if I want to do, say, an apply function. Apply is a concept that comes from Lisp. At least that's where I saw it. In Lisp, you can say, okay, I have a collection of these things, and I want to apply a function to every object in that collection. Okay, a pointer to member allows you to do that kind of thing. It says, you can choose the function that you want to apply, and it can be any function. Of course, it has to match a particular signature, but I will go through and apply that function. So let's take a look at an example of pointers to members. So suppose I have a class called Wampus, and a Wampus can jump and sit and beg. It's got a name. Okay, and once again, my X bag comes in handy because I want to make a bag of Wampuses. So I just inherit it from a template instantiation of X bag, which holds Wampuses. And then I will create an apply function. And notice the argument list of this apply function. This is a pointer to a function which takes no arguments and returns void. But it's more than just a pointer. It's a pointer to a member. Notice that all of the functions here are functions which take no arguments and return void. So any of those can be applied here. So I can apply any of those, and it'll go through from 0 to size and dereference that pointer to function on every object in that array. And we can see how this works we create a wampus bag here and add a bunch of these objects and then call the apply function. So I say, well, apply the jump function, apply the beg function. Again, it's an operator overloading kind of thing. It's syntax convenience. I want to be able to use this sort of syntax, be able to pass it the address of a function which is within the class itself. And this is how you resolve that issue. Another operator that you find is the function call operator. This is kind of unique. It's just like any of the other operators in that the compiler looks at it and it figures out what real function call to make. But it's the operator open paren, close paren. The interesting thing about this one, it's unique among all the operators. Most of the operators, they say, well, you have to have a certain number of arguments. Plus has to have a left argument and a right argument, or it has to be a member that has a right-hand argument. Well, the function call operator can have any number of arguments. And the call to this looks like you've got an object, open paren, the argument's close paren. So again, sometimes the syntax is convenient or logical. So if it is, this is the function call to use. As an aside, the placement syntax for operator new, which we'll see a little later today, also allows for multiple arguments. But those are the only two. Okay, when do you use member operators versus friend operators? In particular, suppose you're defining an operator plus. Should that operator plus be a member or a friend? How do you decide? Well, if you have a friend function, that means it's global. A friend operator plus has two arguments, the first argument and the second argument. The first argument goes on the left-hand side of the plus, and the second argument goes on the right-hand side. If you have a friend function, then the compiler can look at either of those arguments and it can do automatic type conversion on them. If you have a member function, you only have one argument, because the thing on the left-hand side is the object of the current class. Only the thing on the right-hand side can be converted. So this is how you make the decision. Do you want both of the arguments to be automatically type converted, or do you just want the thing on the right-hand side to have automatic type conversion operated on it? So you control the use of the operator this way. Here's apples. So we can add apples to oranges. We create a struct called orange and one called apple. And here is a member operator plus. And here is a friend operator minus. So the member operator plus has one argument because the object or the current class is on the left-hand side of the plus, and the orange is on the right-hand side. The friend operator minus has two arguments. This is the left-hand operator. This is the right-hand operator. We have an automatic type conversion operator here to make an apple out of an orange. And if we do this because of some of the things we need to do, if we create a constructor, any constructor, then the automatic creation of constructors is called off. The compiler won't automatically create constructors for you if you can create any of them. And since I need a default constructor, now I have to explicitly define one, because down here I need a default constructor. Okay, in main, I create an apple and an orange, and I can add an apple to an orange because I have an operator plus here that takes an orange as its second argument. Well, that's real straightforward. I cannot add an orange to an apple because I don't have an operator plus for orange. I can subtract an apple from an apple, which is fine because you see it right up here. That's a direct call. I can subtract an orange from an apple because the second argument can automatically be converted with this constructor into an apple, even though it's an orange. The compiler calls the automatic type conversion operator to turn this into an apple, and then we get an apple minus an apple again. Now, what's interesting is that this also works because orange is simply the first argument of operator minus in this case. So orange can be converted to an apple, and then operator minus works. Now, what's interesting is that even this works. We got an orange, And the compiler can call the constructor to convert both oranges into apples, and then calls the operator minus. So it allows you to open all that syntax up. If you don't want to, think about using function calls first. Only if you really have to use overloaded operators. If it just really helps the situation, then do it.
In the next lesson, get ready to learn some really great programming techniques. What can you do with your old C code? Throw it away? How can you keep track of what your programs are doing at runtime? How can you avoid some of the common C++ problems? In this lesson, Bruce will talk about several programming techniques you can use to improve the quality and robustness of your programs.
One thing I want to talk about is the concept of wrappers, which is simply taking existing C functionality and wrapping it in classes. And in particular, I want to talk about inheriting from C structs, because that's something that didn't occur to me until much later, that since it's a structure, I always thought, well, it was a C programmer that designed this thing, so he or she didn't know anything about C++, and so how could I inherit from that? Well, it turns out that you can inherit from that, and you can do all sorts of nifty and interesting things. We'll see an example of that. Talk about reference counting, which is important. Also, the concept of virtual constructors. There is no support for virtual constructors, and actually there can't be. It's sort of a logical impossibility, but there is a way that you can kind of simulate it if you really want to. The idea of a wrapper is that you're encapsulating a set of C functions. Well, if you look at a C library, it's generally a struct and a set of functions that are associated with that struct. So if you're moving into C++, for example, you don't necessarily want to rewrite all that stuff, but you want the cleanliness of having all this in a class. So you might inherit and wrap a class around this and put your member functions inside of this class. Clean it up, make it neater. Add some safety to it. Of course, you know that a lot of issues in C++ are safety issues. Construction, and destruction, that sort of thing, and also the type checking ensures much better safety. So there are reasons to do this. You benefit from the existing C library, and you don't lose all the work that's been done into it. It's not very hard to convert. And you can put it into an object-oriented framework. As I mentioned before, I discovered that if it's a struct, you can easily inherit from it, and you get some benefits that way because you get automatic creation of constructors. And the example I want to show you, I'll use the find first and find next functions and the struct ff block. Now, together they make kind of a little library. You have an ff block and you have find first and find next that operate on one of those so that you can find all the files given an ambiguous file name. So let's take a look at the example. Okay, what this is a simple directory lister. The first thing that I'm going to do is inherit from ff block the class D file, even though ff block is a struct that was created by a C programmer. What I would like to do is create a copy constructor so that any time an object of type D file is passed by value, the name element is forced to lowercase. So what I will do is define a copy constructor. If you're passing a D file by value, that means you're creating a D file inside of your function frame from an existing D file outside of the function frame. So the copy constructor is called. So here's the copy constructor. And what I'll do is just call the base class copy constructor. Well, that's interesting because the base class is this struct ff block, and I know that a C programmer made that, and they didn't know anything about copy constructors. So what's going on here? Well, what's happening here is that the copy constructor is being created automatically. Remember that if you don't do any of this stuff, the compiler will do it for you. So I am calling the base class copy constructor, and the compiler is creating it for me, and that copy constructor simply does a bit copy of the various members of the FF block. So it just copies everything over. So in this one statement here, I'm doing a copy of all the members, and then I force the FF underscore name, which is the base class data member, to lowercase. So there's some extra stuff going on here. Now, since I create a constructor, I have to define the default constructor if I'm going to use one. And it turns out later on I discovered, gee, I have to have a default constructor, so I came back and put it in. Then I can create an OStream operator left shift to take my dfile object and send it to the output. And notice that this set iOS flags is a manipulator. And the flag that I set to, as I say, left justify it. And I set the width to 15. So these are the kinds of things that you can do to format the output. As I said before, everything that you can do in printf in terms of formatting, you can do with IO streams. And then I print out the name and the size. Now I will make a list of files, once again inheriting from my trusty xbag. So it's going to hold dfile pointers. And I will create a new add function. So what I will add to it is an ambiguous file name, which it will go through and expand with find first and find next. And whenever it finds a name, it's going to add a new dfile object created from file. Now, what do I have here? I have a dfile object, and I'm passing its address to find first. That's interesting because find first takes an FF block as its argument, but I'm passing it an object of a different type, or MI. Dfile is inherited from FF block, therefore dfile is a type of FF block. It's got all the elements that FF block has in it, so I can pass its address to find first, and everything works fine, and it goes in and fills up all the data elements. So that's okay. Now I've got my dfile, and I create a copy of that on the heap to put into my xbag. And when I create a copy of it, I'm making a new dfile from an existing dfile. Therefore, the copy constructor gets called. Therefore, the name of the file is forced to lowercase. So the add function goes through and fills it up. Inside of main, I can simply say I create a file list, and if there are no arguments on the command line, I simply add star.star to the file list. This is expanded to all the file names in the current directory. If there is an argument list, I go through all the arguments and I expand each one. So this isn't just like dir, where you only have one argument. You can say dir star.h, star.cpp, and you can get them all, or whatever I'm calling this function. So the next thing that I do is I want to sum up the number of bytes in the entire list. So I add those all up, and then finally I select each element in the list and I print it out, and I put out the total number of bytes. Okay, so I have a little directory listing program here. Pretty slick. Fairly easy to put together. Okay, what is reference counting? Somebody asked a little earlier today, what happens if I have a class that's got a pointer in it, and for example, I want to copy an object of that class from one place to another. Say I want to pass it into a function, or I want to make a duplicate of it, or want to make a new object from that existing object, say use the operator equals. So what is happening to that pointer? Well, the simplest thing you can imagine, the pointer is just being copied from one place to another. But the pointer is pointing to a chunk of data someplace. So when you copy an object that has a pointer, then you end up with two objects that are pointing to the same piece of data. This is a problem, especially when you call the destructor for one of those objects, and the destructor says, okay, whatever my pointer is pointing to, I better clean up because it's on the heap. And so it gets called, and now the other object is pointing to nothing at all. It's pointing to invalid data. So you can easily see how this would happen. This is my first experience with reference counting. I have an object. It was a matrix. So you got an object, and it's pointing to all the matrix data, and I want to pass this object by value into a function. So the copy constructor is called, and the pointer is duplicated. Now I've got an object inside the function frame and one outside of the function frame, both pointing to the same piece of matrix data. That's fine. Now I get to the end of this function frame. The object goes out of scope. Its destructor is called, and it releases that memory, even though the object outside of the function frame is still ostensibly using that. That's a big problem. So all of a sudden, I'm left with dangling pointers all over the place. So there's two approaches that you can use to handle this. One approach is that every time you make a copy, you can clone the data that it's pointing to. So for example, if you've got a string object and it's got a pointer to a bunch of data, every time you say pass that string by value, you simply clone that data. That doesn't sound so outrageous when dealing with strings. But what I was dealing with was very large matrices. We were trying to model the floor of the ocean. And so we had big data. And you don't want to be cloning this data every time you pass these objects around. So we needed a way to have the data that we're pointing to left alone, not destroyed when these objects are going out of scope. What you do with reference counting requires a little bit of bookkeeping, but it's really not that hard. What you do is you put a reference count in the data that is being pointed to. Then whenever you create a new object of this type that's pointing to this data, when you point your pointer to that data, you increment that data's reference count. Whenever the destructor is called for one of these objects, the destructor decrements the pointer to that, it decrements that reference count. If the reference count goes to 0, that means there are no other objects pointing to that data, and that data can be released. So you can see this is a sort of another situation where people would say, well, if you had garbage collection, it would be very easy. Maybe. Anyway, reference counting, it isn't that hard to implement once you understand the basic concepts. And the places where you have to worry about incrementing and decrementing the count are, in particular, well, the constructor. Any constructor, you're creating the data probably certainly for the first time. Then you set the reference count to 1. So that's one place. The copy constructor, where you're building an object from an existing object, you increment the reference count because the data is already out there. The destructor, you decrement the reference count. And one more place, well, there could be several other places. I mean, for example, if you're adding two objects together, you may end up with a result, or the result of it may be the data in one of those objects. Depends on how your architecture works. But one other very important place is the operator equals. Because if you're assigning something to something else, that's probably the trickiest place. Suppose you have two objects, both of which point to blocks of data. Okay, I want to assign this object to this object. So the first thing I have to do is, since I'm taking this, which is pointing to a piece of data, and I'm assigning it to over here, and so I'm going to point to its data, is I had better, well, not delete the data I'm pointing to, but decrement its reference count, and if the reference count goes to 0, then delete it. Okay, so I've cleaned up the old data that I'm pointing to. Now I want to assign it to the new object. So I do the assignment, and then I increment its reference count, because now one more object is pointing to that chunk of data. So the operator equals is probably the trickiest bit, because you have to clean up what you used to point to before you're pointing to something new. But once you take care of all of those, then reference counting is taken care of, and you won't lose an object prematurely. This class block represents the data chunk that we're pointing to. So it's some big chunk of data. Oh, actually, class block is the object itself. Struct data is the chunk of data that it's pointing to. And that contains a reference counter and whatever data it is you're pointing to. So block contains a pointer to this data object. When I create one, I allocate the object itself, and then I set the reference count to 1 because I'm the only object using it. I just allocated it, so I'm using it. The copy constructor says that I've got an existing object, and I'm going to create a new object using the data in that existing object. So I take my data pointer, and I point it to the existing object's data pointer. And then I increment the reference count to the chunk that I just stuck my pointer onto. So now there's an additional object using it. The one that I said was trickiest was the operator equals. So I'm going to assign an object of my type, a block, to an existing block. So what I have to do is, first, I decrement the reference count on the data that I'm currently pointing to. If it goes to 0, I delete it because nobody else is using it. Then I assign my data pointer to the thing on the right-hand side of the equal sign, its data pointer, the R-value data pointer. And then I increment its reference count. And as you usually do with an operator equals, I return the address of the current object. Finally, the destructor, I decrement the reference count, and if the reference count goes to 0, I delete the data object. But if it doesn't, I don't do anything because other objects are using it. That's reference counting. So in a situation where we have pass by value like this, we've got an object of type block outside the function scope. We want to pass it inside the function frame, and then at the end, at the closing brace, that local object is going to be destroyed. A and B each get their own memory. I pass this B to F. The copy constructor is called. The destructor is called. B still points to live data because I'm using reference counting. If I hadn't done reference counting, it wouldn't have worked right. After the end of this function call, the destructor for the local object inside of F would have been called, and it would have cleaned up. It would have removed that pointer. It wouldn't have worked right. OK, what's a virtual constructor? There's only one function in C++ that cannot be virtual, and that is the constructor. Why is this? Well, there's a number of different ways to look at it. A virtual function says, I don't know what type you are, but do the right thing anyway. A constructor is the creation of an object of a specific type, and the compiler has to know the specific type of the object because it's installing the v-pointer in there. Before that object has been created in its exact type, there's no way to do a virtual function call. Only after the constructor has completed is the object ready to have a virtual function called for it. What's happening inside of the constructor is that the compiler is setting the v-pointer to the proper v-table. To know what the proper v-table it is, it has to know the exact type. The v-pointer has to be initialized before you can make a virtual function call. So as a result, there isn't any late binding that happens inside of the constructor. That can occur because the constructor is still the base class constructor, and late binding assumes that you're going out into one of the derived classes and calling a function which may assume that certain things have been initialized already. And since you're in the base class constructor, you haven't built the whole object up, and it would be very dangerous to be making a virtual function call. So for all these reasons, the idea of a virtual constructor is sort of anathema to what we're... I mean, it doesn't fit. However, what does a virtual constructor conceptually mean? Why would you want to use them? Well, what you're trying to do is say, object, I don't know what type you are, but do the right thing anyway, even as the object is being created. Well, what does the constructor do? It effectively creates the object. So what you're trying to do is say, object, I don't know what type you are, but create yourself correctly anyway. That's why it's kind of hard to think about. Sometimes you'd like to do that. As an example, I've played with the idea of parsing programming languages for a while now. And what would be really nice is for me to just grab a bunch of, turn things into tokens, and then take a token and pass it and say, OK, make the right kind of object based on whatever this token is. And so that's sort of the idea of a virtual constructor. Say, OK, here's an open brace. Make the correct type of token. Here's this. make the correct type of token. So you've got so many options here. You just like to toss it at some function, and the function would automatically create the right type of object. And what you would get back is a pointer to the base class. And so then you could deal with everything polymorphically. A nice idea. Then I started thinking, well, why does it have to look like a constructor? Why can't it just be a function that I throw some information at that produces a pointer to this base class? It doesn't have to be a constructor. All you want is a function to do this for you. So I came up with what I call an object maker function, which is just like it sounds. I throw some information at it. It creates an object of the correct type. It returns a pointer to, say, if I'm making circles and squares and triangles, I throw it the information. It returns a pointer to a shape. So from then on, I don't have to worry about what specific type it is. I deal with it polymorphically. OK, let me show you the example. What I'm going to do in this example is I will have a pointer inside of the object. And that pointer will point to the actual object that I'm going to deal with. This is just a little wrapper. James Copeland calls this envelopes and letters. So he creates an object which is simply an envelope, and it has a pointer to the letter which has got all the meat in it. And the envelope is just this little shell. Sometimes people call this pluggable pointer composition because you can change what the pointer points to in midstream. So you can change sort of the behavior of the object midstream. We're combining several concepts in one. I'll look at the virtual constructor, simple version of virtual constructor. So I have a struct called a shape underscore. It has functions to draw, erase, and the destructor. I will create a macro which inherits from shape underscore to create an arg. Here we have a circle and a square and a line. I'm just saving myself typing in errors here. So each of these things simply, if I call draw or erase, it simply says you're drawing a circle or you're erasing a circle, etc. So I create a bunch of these shapes, all inherited from shape underscore. And now I make this sort of envelope class for shape, and it contains a shape underscore pointer. And in the constructor, I take as its argument this shape underscore pointer, and I simply assign it to my internal pointer. And then once I've done that, see, by the time I get this shape underscore pointer here, it's been constructed. And so if I call the draw function for it, I'll get the late binding effect. Everything will work fine. In fact, what I'll do is I'll simply change these functions so that the draw function simply calls the draw function for the internal pointer, the erase, etc. So you do that with all of your functions. And then I also have a function which I call transmogrify, inspired by Calvin and Hobbes, with the cardboard box that's the transmogrifier. So what transmogrify does is it takes a shape pointer as its argument, and it erases the old shape and deletes it. And then here's the pluggable pointer composition. So this is after I've got a live object. I can change the way that object behaves by using the transmogrify function. So now its draw is something different. This is useful. I remember one of the first questions a friend of mine asked me. He was studying for a PhD at Cornell, and he was just learning C++, and I don't know what language he had been using, but for some reason the first problem that he wanted to solve was to change a rabbit into a chocolate rabbit or something like that. Can you do that with C++? And that threw me for a loop. For one thing, I didn't know why you were doing that, but also I didn't know how. But now, since I know about transmogrify, I can change a rabbit into a chocolate rabbit. If you really, really want to do something like a virtual constructor, here's how I would do it. Here's creating all these objects. And in the constructor, I say new circle, new square, new line. You have to give it some information to tell it how to create this object. So I figured, give it all the information and let it plug that pointer in. So I make a bunch of shapes. And whenever I call the draw function, that gets relayed to the internal pointer. And at the same time, when I create this object, the constructor calls the draw function and puts it up on the screen. Now that can be useful, because you would like your constructors to draw the objects on the screen, and you'd like the polymorphism to work. So this is a way for that to happen. And then here's how I transmogrify something, whatever it is, into a line. Actually, I'd say this is probably the simplest and safest approach if you really want something to act that way.
The workbook also covers several C++ debugging techniques that you can use to find those particularly tasty bugs. Errors happen. We all know it. What do you do if a constructor fails? What if your program calls a failed object's virtual function? What's needed is a way to handle errors that happen at runtime. The good news is that C++ provides exception handling right in the language with try, throw, and catch keywords.
Exception handling will change the way you program. It'll change the way you think about programming. An exceptional condition is a disastrous situation where you cannot continue processing. The programmer may be tempted to continue processing or tempted to pretend that things are okay, and what you need to do is a way to reach out from inside of your library, because remember, libraries are what we're trying to create so that we can quickly pull together lots of libraries and make applications. So right now, if you create a C struct and a bunch of functions that work with that struct, if the user chooses to ignore the return value from one of your functions, what can you do? Well, with exception handling, you can reach out and you can grab them by the throat and shake them and say, stop what you're doing, this is important. And if they choose to ignore your exception, you can still force something to happen. So this is important. You want the program not to die, preferably. C, on the other hand, kind of assumes that errors won't happen, or they can be easily handled by checking a return value, possibly a global flag that you set inside of your function. One of the problems is, what if your function value is used somehow? Maybe you can't return an improbable value. Then you have to set a global flag. It's kind of awkward. The thing is, any failure is difficult to handle because you build your world assuming that there's a particular control flow, and then you have to start thinking, well, what if this happens? What if that happens? Exception handling is designed to deal with that sort of thing. Okay. Now, when you're inside of a function, and suppose you're inside of a function, you have several objects that you're creating. So you create object 1, you create object 2, and all of a sudden you hit an exceptional situation. You say, I got to get out of here. I can't continue processing here. Now in C, if you get yourself down into a bad situation and you want to be able to go back to a known good state, you use a non-local go-to. A local go-to, you know what it is. You've got a label, you say go to that label, and you jump to it. Simple enough. Well, what if you want to jump out of the current scope into a completely other scope? You can use a non-local go-to, which is implemented with set jump and long jump. With set jump, you say, okay, I'm in a nice warm fuzzy place. I want to remember this, so I will do a set jump. Do a set jump, and you have a structure called a jump buff, and it's remembering this wonderful place you're at. Okay, you work your way down into a messy situation. You say, there's no place like home, there's no place like home. You know. So what happens is the Ruby slippers take you back to your nice warm place with a long jump. Okay, in C this is great because C has a very limited view of the world. And non-local go-tos are very useful in other situations. They're not just for error recovery. They're good for, well, actually, a year and a half ago or so, I wrote an article in computer language which I used set jump and long jump to do task switching. So I created these little task classes, and you could switch from one task to another, and the set jump and long jump took care of that. So they're useful for other reasons. The problem with set jump and long jump is that they simply take you, pick you up out of where you are, and put you someplace else. Well, suppose we're doing our little constructor scenario here. We've got constructor A is called, constructor B is called, and we have trouble, and we do a long jump out of there, well, the destructor for A never gets called. And of course, if you tried to do it some other way and you say, well, if I'm getting out of here, I'll just call all the destructors. Well, you never finished B and you never got to C. So if you call their destructors when they were never constructed, if you were even able to do that, you would be in trouble. So it becomes a very messy situation because you have constructors and destructors. So in C++, we need something different. Set jump and long jump are really too primitive to accomplish our needs. And inside of our class, we can't assume that the user is paying attention to this kind of thing. So we've got to be able to terminate or notify something outside of this scope so things get taken care of properly. Okay, so we do this with C++ exceptions. A C++ exception is like an alternate return mechanism. So if you create a function has a return value. So you might be dividing one thing with another, and so the result might be an integer. Okay, well, what happens if you run into a problem with C++ exceptions? You can say, well, I don't care about returning an integer anymore. That's not even the point. The point is to get out of here safely. So what you do is you can throw an exception. So if you have a class called up, you can say throw up. Anyway, you throw an exception, and you can throw any type out of that class. It's like an alternate return mechanism, and you have an alternate type that you can return from this. You can throw an error, you can throw a char string, you can throw any type that you want. So basically you create classes that represent these error types, and you throw one of them out depending on what type of error you run into. One of the things you might want to return is a divide overflow string. Any number of types you can throw from this. And the nice thing about exception handling is if you're in a function and you hit some constructor calls, and in one of them you have a problem, and you throw out of that all the objects which the constructors have been successfully called for, the destructors are called for those objects, but any object where the constructor has not been called, no destructor is called for that. So everything cleans up nicely. It's really an alternate way to go out of a scope. There are keywords throw, try, and catch. So you throw an exception from inside the place where you have trouble, and you catch the exception someplace else. So what you want to do is you want to surround all of the suspect code in a try block. So you say try, open brace, all of your code. Inside one of the constructors or inside one of the function calls or whatever, you might throw an exception. So at the close of the try block, you have something called a catch clause. So you say catch char string. That is, if something inside of this try block threw a character string out, this is where you end up. And if it's a character string, you can take that string and print it out and do something. And then the next catch, it's like a big switch statement. The next catch phrase might say catch and an object of class error. And you can extract information from that error and do something with it. And so you have several catchphrases. So let's look at a simple example. So I'm going to create a class to represent overflow errors. And it has a constructor which takes 2 float arguments. And then I'm going to create a function called myDiv, which it's my version of a divide function. It takes 2 arguments, floats a and b. And I check to see if b is equivalent to 0. Here's the first exception that I'm going to throw. And this is throwing a char pointer exception. So it's just throwing division by 0. Now I create a string s, which has a destructor. If I throw out of here, this destructor won't be called. The second test, I'm going to say if a is too big or b is too small, then throw one of these overflow objects and give it its arguments here, whatever arguments the constructor for that overflow object wants. So here is a second way to leave this scope. The first way returns a char pointer. The second way returns an overflow object. And if all those things are okay, then I'm going to return from the function normally. Some of you may look at this and be tempted to say, oh, wow, there's all kinds of nifty things you could do with exception handling because it's an alternate return mechanism. Don't. Okay, so let's look at the try block. Inside of a try block, you can have any number of statements. Here, I'm just going to put one function call. Now, this function call may execute successfully, in which case we go to the end of all the catchphrases and continue processing. However, it may throw a care pointer, in which case I'll end up in the catchphrase for the care pointer, and I print out this. It may also throw an overflow object, in which case I'll end up here. And if I do, then I can do some other piece of code to handle overflows. So it's a different kind of a syntax, means your programming is going to be different, but there's some questions that come up here. Okay, one of the questions is, what happens if the user doesn't pay attention to the fact that you've got exception handling? In that case, there's a function that ends up being called, well, the throw continues out of this block until it hits an appropriate catchphrase. If it never finds a particular catchphrase, it ends up in a function called, it's the default handler. And you can change the default handler to do whatever you want to. There's another issue here, which is, how do you know, as the user, if you get a library from somebody else, how do you know what exceptions you should try and catch? And these exceptions are enumerated in the throw specification for a function. So you give, and the throw specification appears in the function declaration. So you would say int foo, the argument list, and then before the closing semicolon or the opening brace, you give the throw specification. So you say throw, open paren, type that it can be thrown, comma, other type that can be thrown, comma, other type that can be thrown, close paren. Any of the types that can be thrown should go in the throw specification, which go in the function declaration. So anybody can look at this and they can say, well, I better catch any of these things. Now, it is considered bad form if you create a throw specification and later on you throw something out that hasn't been specified in the throw specification. And hopefully compilers in the future will enforce or suggest that you don't do that, because it's sort of like lying to the user. You say, I'll throw these three things, and then you throw something else. So exception handling is really a different way to think about handling errors. And it's a much, well, it appeals to me a lot. I think it's a much safer way to deal with these things. And the nice thing about it is that you can build this stuff into your library and you can make sure that an exception gets handled. And you can give the user a clear interface as to what might happen when things go wrong.
Time to go to the workbook one last time and follow the exercises on exception handling. While you're there, you should check out Chapter 9 that covers the latest information about the C++ language. I hope this course has been helpful in getting you beyond the basics of C++. Thanks for joining us.